Look up at the night sky. Right now, as you're hearing these words, something impossible is happening somewhere in the universe. Something that defies every intuition you've ever had about how reality should work. And the beautiful, terrifying truth is this: the cosmos doesn't care about your intuition. Let me take you on a journey to the edges of impossibility, where the universe reveals itself to be stranger than we ever imagined, stranger perhaps than we can imagine. Because out there, in the darkness between stars, in the hearts of collapsed giants, in the fabric of space-time itself, nature is performing experiments that make our wildest science fiction look like child's play. You know what fascinates me most about the universe? It's not that it's big. Sure, it's incomprehensibly vast, containing more stars than grains of sand on every beach on Earth. But size alone isn't what keeps me awake at night. What keeps me awake is that the universe is weird. Beautifully, magnificently weird. And nowhere is that weirdness more apparent than in the phenomena we're about to explore together. Consider this. Right now, there are objects in space so dense that a teaspoon of their material would weigh as much as a mountain. There are storms raging on distant worlds that have lasted for centuries, with winds that would tear apart anything we've ever built. There are galaxies colliding in slow-motion catastrophes that span millions of years. There are jets of matter shooting out of black holes at nearly the speed of light, stretching across thousands of light years. And perhaps most unsettling of all, there are vast regions of space that are quite literally tearing themselves apart, driven by a mysterious force we call dark energy but don't really understand at all. Let's start with something that sounds impossible. A star that shouldn't exist. KIC 8462852. You might know it better as Tabby's star, named after astronomer Tabitha Bayagian, who first noticed something peculiar about it. This star, about 1,470 light-years away from Earth, does something no star should do. It dims, dramatically, irregularly, sometimes by up to 22%. Now, you might think, so what? Stars dim all the time, right? Wrong. When a planet passes in front of a star, causing what we call a transit, the star dims by maybe 1%, maybe less. Jupiter, the largest planet in our solar system, blocks about 1% of the sun's light when it transits. So what could block 22% of a star's light? What could be so massive, so enormous, that it could swallow nearly a quarter of a star's luminous output? Here's where it gets interesting. The dimming isn't periodic. It's not regular. It's chaotic. Sometimes the star dims by a little, sometimes by a lot. Sometimes it stays bright for months. Then suddenly, without warning, it goes dark again. This isn't the behavior of a planet. This isn't the behavior of anything we've seen before in over 200,000 stars observed by the Kepler Space Telescope. The initial suggestions were wild. Some scientists proposed a massive swarm of comets, broken apart by the gravity of a passing star, now orbiting Tabby's star in a chaotic dance. Others suggested we were seeing the aftermath of a planetary collision, watching as debris clouds periodically block our view. And yes, there were those who whispered about megastructures, vast constructions built by an advanced civilization harvesting the energy of their star. A Dyson swarm, they called it, imagining massive solar panels orbiting the star, converting starlight into usable energy. The truth, as we understand it now, is probably less exotic but no less fascinating. The most likely explanation involves dust, vast clouds of it, orbiting the star in complex patterns. But here's what I love about this: we don't know for sure. Even now, with all our telescopes and all our instruments, Tabby's star keeps its secrets. It reminds us that the universe is under no obligation to make sense to us. It was here long before we arrived, and it'll be here long after we're gone. We're just visitors trying to understand the rules of a game that's been playing for 13.8 billion years. But let's talk about something even stranger. Let's talk about magnetars. Imagine taking the entire mass of our sun and compressing it down into a sphere about 20 kilometers across. Already, that's insane. That's a neutron star, an object so dense that the atoms themselves are crushed, their electrons forced into the protons to create a ball of pure neutrons. A sugar cube-sized piece of neutron star material would weigh about 1 billion tons. Let that sink in. A sugar cube, 1 billion tons. Now, take that already impossible object and give it the most powerful magnetic field in the known universe. A field so strong that it defies description. We're talking about magnetic fields of 10 to the power of 15 Gauss. For comparison, Earth's magnetic field is about half a Gauss. A strong refrigerator magnet might be 100 Gauss. An MRI machine, powerful enough to rip metal objects across a room, generates about 10,000 Gauss. Now multiply that by 100 billion. That's a magnetar. What does a magnetic field that strong do? It breaks the laws of physics as we normally understand them. It polarizes the vacuum of space itself. Empty space, which we think of as nothing, becomes something in the presence of a magnetar's magnetic field. The quantum foam of virtual particles that constantly pop in and out of existence suddenly become aligned, organized. Space itself becomes magnetic. If you were somehow able to get within 1,000 kilometers of a magnetar, and I want to be clear that you absolutely could not survive this, the magnetic field would be strong enough to disrupt the molecular bonds in your body. You would literally cease to be held together at a molecular level. The proteins in your cells, which rely on tiny quantum mechanical interactions to maintain their shape and function, would be torn apart. You wouldn't just die. You would stop being you in any meaningful sense. You would become a cloud of disconnected atoms. But it gets better, or worse, depending on your perspective. Magnetars throw tantrums. Every once in a while, their crust, made of crystallized nuclear material, cracks. When this happens, it releases a burst of energy called a hyperflare. In December of 2004, a magnetar called SGR 1806-20, about 50,000 light-years away from Earth, had one of these outbursts. In 1/10 of a second, it released more energy than the sun produces in 100,000 years. For that brief moment, it was the brightest object in the universe outside of our own galaxy. That burst of energy, traveling at the speed of light for 50,000 years, hit Earth. Even at that distance, even after traveling across half the galaxy, it was powerful enough to disrupt our ionosphere, the same ionosphere that radio communications depend on. If that magnetar had been just 10 light-years away instead of 50,000, it would have sterilized Earth. Completely. Every living thing, every bacterium, every extremophile clinging to life in the deepest ocean vent, gone. The ozone layer would have been destroyed. The atmosphere would have been partially blown away. Earth would have been rendered uninhabitable in less than a second. And here's the truly sobering thought. There might have been planets around that magnetar. There probably were. They're gone now. Not just lifeless. Gone. Vaporized. The hyperflare would have stripped away their atmospheres, melted their surfaces, potentially even torn them apart entirely. If there was life on any of those worlds, it never knew what hit it. It died at the speed of light, killed by its own star's death throes. This is the universe we live in. Beautiful, yes. Life-giving, certainly, at least in our little corner of it. But also violent beyond imagining, capable of casual destruction on scales we can barely comprehend. Now let me tell you about something that happened in 2017 that fundamentally changed our understanding of the cosmos. On August 17th at 12:41 and 4 seconds Universal Time Coordinated, something remarkable occurred about 130 million light-years away from Earth, in a galaxy called NGC 4993. Two neutron stars, each about 1.4 times the mass of our Sun, each compressed into a ball barely 20 kilometers across, completed a dance they'd been performing for hundreds of millions of years. They'd been orbiting each other, spiraling inward, losing energy to gravitational waves, ripples in the fabric of space-time itself predicted by Einstein over a century ago. With each orbit, they got closer, faster. The speed increased. The gravitational waves intensified. And then, in a cataclysm that lasted less than a second but changed everything, they collided. For the first time in human history, we saw this collision with our own eyes. Not just detected the gravitational waves, though we did that too, using the LIGO and Virgo detectors that can measure changes in distance smaller than 1,000th the diameter of a proton. But we also saw it with light. Telescopes all over the world, from gamma-ray detectors in space to optical telescopes on the ground, swung into action. We watched as the collision produced a kilonova, an explosion that made a supernova look tame by comparison. And here's what blew my mind when I first understood it. We watched the universe making gold. Right there, in real time, well, real time minus 130 million years for the light travel time, we observed the birth of heavy elements. Everything heavier than iron on the periodic table, all of it, is made in events like this. The gold in your wedding ring, the platinum in your car's catalytic converter, the uranium in nuclear reactors, even the iodine in your thyroid gland, all of it was forged in the collision of neutron stars. Think about that. The atoms in your body right now, the calcium in your bones, the iron in your blood, the carbon in your DNA, they're all made of star stuff, as Carl Sagan so eloquently put it. But the really heavy stuff, that came from something even more extreme. It came from a collision so violent, so energetic, that it literally squeezed protons and neutrons together through sheer force, building up elements that cannot be created any other way. We are not just made of star stuff. We're made of neutron star collision stuff. We're made of the debris of the most violent events in the universe. And somehow, incredibly, impossibly, those atoms came together in just the right way to make you. To make a creature capable of looking back at the cosmos and understanding where you came from. That's not just amazing, that's humbling. But let's talk about something that's happening right now all around us that we can't see, can't touch, can't interact with in any meaningful way, and yet makes up about 85% of all the matter in the universe. Dark matter. I love this term because it's both accurate and completely unhelpful. It's dark because it doesn't emit, absorb, or reflect light. It's matter because it has mass and gravity. And that's about all we know for certain. Here's the evidence: galaxies spin. When we measure how fast stars orbit around galactic centers, they're moving too fast. Way too fast. Based on the visible matter we can see, the stars, the gas, the dust, galaxies should tear themselves apart. The outer stars should fly off into intergalactic space like water flying off a spinning wheel. But they don't. Something is holding them together. Something with mass. Something with gravity. Something we can't see. We can see its effects. When we look at galaxy clusters, we can see gravitational lensing, where the light from background galaxies is bent and distorted by the gravity of the cluster. But when we add up all the visible matter in the cluster, all the stars and gas, there's not nearly enough mass to produce the lensing we observe. Something invisible is bending space-time. Something massive is there, pulling on light itself, but completely invisible to every telescope we've ever built. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical particles that barely interact with normal matter at all. Billions of them might be passing through your body right now, streaming through the Earth like ghosts, unaffected by the atoms and molecules that make up everything you've ever known. We've built detectors deep underground, shielded from cosmic rays, cooled to nearly absolute zero, waiting for the incredibly rare event when a dark matter particle might collide with a normal atom. So far, despite decades of searching, we've found nothing conclusive. And maybe that's the point. Maybe dark matter is nature's way of reminding us that we don't know everything, that the universe is bigger, stranger, more complex than any theory we've yet devised, that the matter we're made of, the stuff we can see and touch and measure, is actually the unusual stuff. We're the minority. We're the weird ones. Normal matter, the stuff of stars and planets and people, makes up only about 15% of the matter in the universe. The rest is dark matter, invisible, mysterious, fundamentally different from everything we know. Let me take you to one of the most violent places in the universe, the center of a supermassive black hole's accretion disk. We're talking about a black hole millions or billions of times the mass of the sun, surrounded by a disk of material spiraling inward, doomed. As matter falls toward the event horizon, It accelerates, heats up, becomes so energetic that it glows. But not just glows. It screams. It emits X-rays. It generates magnetic fields that could contain entire solar systems. And sometimes, in ways we still don't fully understand, it launches jets. These jets are among the most powerful phenomena in the universe. Streams of matter and energy, accelerated to 99% the speed of light or faster, shooting out perpendicular to the accretion disk. Some of these jets stretch for hundreds of thousands of light years, longer than the diameter of most galaxies. They carry more energy than a billion supernovae. They can be detected from across the observable universe. The black hole at the center of the galaxy M87, the same black hole we famously imaged in 2019, showing that iconic first picture of a black hole's shadow, has a jet stretching 5,000 light-years into space. 5,000 light-years. That's more than the distance from Earth to the center of our own galaxy. And that's just a medium-sized jet. The galaxy Hercules A has jets stretching over 1 million light-years, each one containing the mass of 1 billion suns worth of material. What's powering these jets? The black hole itself isn't emitting anything. By definition, nothing can escape from beyond the event horizon. But the material just outside the event horizon in the accretion disk is in a state beyond anything we can reproduce on Earth. Temperatures of millions of degrees, densities higher than the core of the sun, magnetic fields that make a magnetar look weak. And somehow, through processes we're still working to understand, this material gets collimated, focused, accelerated, and shot out into space at relativistic speeds. These jets can have profound effects on galaxies. When they plow through intergalactic gas, they heat it up, preventing it from collapsing to form new stars. They can shut down star formation across an entire galaxy, essentially killing it, turning it from a vibrant, star-forming spiral into a dead, quiescent elliptical. The supermassive black holes at the centers of galaxies, paradoxically, regulate how many stars their host galaxies can make. Too much black hole activity, too powerful a jet, and star formation stops. Not enough, and the galaxy might form stars too quickly, exhausting its gas supply. It's a delicate balance, a cosmic ecology where the most destructive objects in the universe, black holes, play a role in determining the fate of galaxies. And remember, every large galaxy has one of these at its center, including ours. Sagittarius A-, the 4 million solar mass black hole at the heart of the Milky Way, is relatively quiet now, but it hasn't always been. There's evidence of massive outbursts in the past, bubbles of hot gas expanding above and below the galactic plane, the signature of ancient jet activity. Our galaxy's central black hole was once a monster. It might be again. Now, let's venture to the edge of the solar system, to a place where the sun's light is so faint it's barely distinguishable from other stars, where temperatures hover just a few degrees above absolute zero, where ice comes in varieties we don't even have names for. I'm talking about the Kuiper Belt and the Oort cloud, vast reservoirs of icy bodies that orbit our sun at incredible distances. Pluto, demoted from planet status in 2006 much to the dismay of people who grew up memorizing 9 planets, is a Kuiper Belt object. It's one of thousands, possibly hundreds of thousands, of icy bodies orbiting beyond Neptune. We've only seen a tiny fraction of them. New Horizons, the spacecraft that flew by Pluto in 2015, giving us our first close-up look at this distant world, showed us something extraordinary. Pluto is geologically active. It has ice mountains made of water ice as hard as rock in those temperatures. It has nitrogen glaciers that flow like liquid, creating a vast, smooth plain called Sputnik Planitia. It has a thin atmosphere that freezes and falls to the surface as snow. Pluto shouldn't be active. It's too small, too far from the sun. It should have frozen solid billions of years ago, its interior cold and dead. But it's not. Something is heating it from within. Possibly radioactive decay. Possibly tidal interactions with its moon Charon. We don't know for sure. What we do know is that even in the coldest, most remote reaches of our solar system, worlds can surprise us. And beyond the Kuiper belt lies the Oort cloud, a spherical shell of icy bodies surrounding the solar system, extending perhaps a light year from the sun, halfway to the nearest star. We've never seen the Oort cloud directly. We can't. The objects are too small, too far, too dark. But we know it's there because of comets. Long-period comets, visitors from the outer solar system that swing through the inner solar system on orbits lasting thousands or millions of years, come from the Oort cloud. Something disturbed them, perhaps the gravity of a passing star, perhaps the general gravitational field of the galaxy itself, and sent them falling toward the sun. These comets are time capsules, preserving the original material from the solar system's formation 4.5 billion years ago. When we study comets, we're studying the building blocks of planets, unchanged by billions of years of geological activity. We've even landed on a comet. The Rosetta mission's Philae lander touched down on Comet 67P in 2014, the first time humanity has ever soft-landed on a comet. We've analyzed cometary material directly. We've found organic compounds, complex molecules that might be precursors to life. We've found that comets contain water, though not quite the same isotopic signature as Earth's oceans, complicating the idea that comets delivered all of Earth's water. But here's something strange. In 2017, astronomers discovered an object passing through the solar system that didn't belong. Oumuamua, a Hawaiian word meaning scout or messenger, was the first confirmed interstellar object ever observed. Came from outside our solar system, passed through and left, never to return. And it was weird. First, its shape. Based on how its brightness varied as it tumbled through space, Oumuamua appeared to be highly elongated, perhaps 10 times longer than it was wide. No natural object we'd ever seen had that shape. Comets are roughly spherical. Asteroids might be a bit elongated, but nothing like this. Second, its motion. As Oumuamua moved away from the sun, it accelerated slightly more than gravity alone could explain. Comets do this all the time. As they heat up, ice vaporizes, creating a jet that acts like a tiny rocket, pushing the comet slightly off its gravitational trajectory. But Oumuamua showed no signs of outgassing. No coma, no tail, nothing that would indicate it was a comet. Yet it accelerated anyway. The most likely explanation, and I want to emphasize that this is the most likely, is that Oumuamua was a comet, but one covered in a layer of organic material that insulated the ice beneath, preventing the kind of obvious outgassing we associate with comets. When the ice did vaporize, it escaped through cracks or vents that we couldn't resolve from Earth, creating thrust without creating a visible coma. But other explanations have been proposed. Some scientists, notably Harvard astronomer Avi Loeb, have suggested that Oumuamua's acceleration could be explained if it were incredibly thin and light, like a solar sail, pushed by the pressure of sunlight itself. And if it's a solar sail, well, solar sails are technology. That means someone built it. That means we might have just witnessed our first encounter with alien technology. Now, I'm skeptical. I think the boring explanation is probably correct. Oumuamua was a comet, just a weird one, and the universe has billions of years and trillions of opportunities to create weird comets. But I also think it's important not to dismiss the possibility out of hand. We should be looking for more interstellar objects. We should be studying them more carefully. Because if, and this is a big if one of them turns out to be artificial, that changes everything. Let me tell you about fast radio bursts, or FRBs. These are some of the most puzzling phenomena discovered in the last couple of decades. They're exactly what they sound like: extremely bright bursts of radio waves that last for just a few milliseconds. In that brief moment, an FRB can output as much energy as the sun produces in several days. And then it's gone. The first FRB was discovered in 2007, though it had actually occurred back in 2001 and was found in archival data. It was called the Lorimer burst, after astronomer Duncan Lorimer, who discovered it. For years, it was a curiosity, a one-off, maybe an instrumental glitch, maybe a terrestrial signal that somehow contaminated the data. But then we found more, dozens more. Now we've detected thousands of them. Here's what's strange. Most FRBs are one-offs. They flash once and are never seen again. The source, whatever it is, emits this incredible burst of energy and then goes silent, perhaps forever. A few FRBs repeat. These repeaters are particularly interesting because we can study them in more detail. We can point multiple telescopes at the source and wait for the next burst. One repeating FRB, FRB 121102, has been localized to a dwarf galaxy about 3 billion light-years away. That's a helpful piece of information. It tells us these events are extragalactic, truly cosmic in scale. It also tells us they're associated with galaxies, which means they probably have something to do with stellar phenomena. But what? The leading theories involve magnetars, those ultramagnetic neutron stars we talked about earlier. Perhaps the magnetic field lines on a magnetar occasionally reconnect, releasing enormous amounts of energy in a brief flash. Or perhaps FRBs are caused by neutron stars collapsing into black holes, their final cry before disappearing behind an event horizon forever. Or maybe there's something else entirely, something we haven't thought of yet. And then there's the truly wild speculation. Could FRBs be artificial? Could they be signals from an advanced civilization, perhaps using radio bursts to propel spacecraft equipped with light sails? The energy requirements would be enormous, but so what? An advanced civilization capable of harnessing the energy output of a star could do it. We would detect these propulsion beams as FRBs. I don't think that's what FRBs are. The evidence points toward natural phenomena. But the fact that we can even ask the question, that we've discovered something so energetic and so brief that we have to consider all possibilities, that's what makes this exciting. That's why I love astrophysics. Every answer leads to new questions. Every discovery reveals new mysteries. Let's talk about something that sounds like science fiction but is absolutely real. Hypervelocity stars. These are stars moving so fast they're escaping the galaxy entirely. We're talking about speeds of 1,000 kilometers per second or more. That's over 2 million miles per hour. At that speed, you could travel from Earth to the Moon in less than 2 minutes. How do stars get moving that fast? The most common mechanism involves close encounters with the supermassive black hole at the galactic center. Imagine a binary star system, 2 stars orbiting each other, wandering too close to Sagittarius A-. The black hole's gravity tears the binary apart. One star is captured, destined to eventually fall into the black hole. The other star is flung away, like a stone from a slingshot, carrying the orbital energy of the original binary system. It shoots out of the galactic core at incredible speed. We've found dozens of these hypervelocity stars. Most are heading out of the galaxy, destined to spend eternity in the vast, cold emptiness of intergalactic space. Some will travel for billions of years before their nuclear fuel runs out. They'll die alone, far from any other stars, their light taking millions of years to reach the nearest galaxy. But here's something to think about. If our sun were a hypervelocity star, if it were flung out of the galaxy, what would the night sky look like? There would be no Milky Way, no band of light across the sky representing our galaxy seen edge-on. Instead, the Milky Way would be an object, a spiral galaxy hanging in the distance, slowly receding as we moved away at incredible speed. The night sky would be mostly empty, just a few nearby galaxies, Andromeda, the Magellanic Clouds, and the vast darkness of intergalactic space. If life somehow evolved on a planet around a hypervelocity star, would those beings know they lived in a galaxy? Would they understand they were outcasts, exiles, flung from the stellar metropolis to the cosmic countryside? Or would they think their isolation was normal, that all stars lived alone in the darkness? Now, let me take you somewhere truly bizarre. The South Atlantic Anomaly. This isn't in deep space. It's right here, orbiting Earth. It's a region of space a few hundred kilometers above the Earth's surface where the Van Allen radiation belt dips down closer to the planet. The Van Allen belts are zones of charged particles, mostly protons and electrons, trapped by Earth's magnetic field. They're dangerous. Too much radiation. Spacecraft and satellites have to be built to withstand them. Astronauts try to pass through them as quickly as possible. In most places, the inner Van Allen belt is about 1,000 kilometers above Earth's surface. But over the South Atlantic, due to a quirk in Earth's magnetic field, it dips down to just 200 kilometers. Satellites passing through this region get hit with much higher radiation doses. Computers malfunction. Sensors give false readings. The Hubble Space Telescope has to shut down its instruments when passing through the anomaly to avoid damage. Why does this happen? Earth's magnetic field isn't perfectly aligned with its rotational axis. The magnetic poles don't match the geographic poles, and the magnetic field itself isn't perfectly symmetrical. There's an offset, a tilt, and the result is this weak spot over the South Atlantic where radiation that should be trapped high above Earth can penetrate much deeper. And it's growing. The South Atlantic anomaly has been expanding and intensifying over the past few decades. This might be related to the gradual weakening of Earth's magnetic field, which has decreased by about 6% over the past century. Some scientists think we might be witnessing the early stages of a magnetic pole reversal, an event where Earth's magnetic north and south poles flip. This happened before, many times throughout Earth's history. The geological record shows magnetic reversals occurring every few 100,000 years on average, though the timing is irregular. What happens during a reversal? We don't know exactly. The magnetic field doesn't disappear, but it weakens significantly and becomes more complex, with multiple north and south poles appearing temporarily. The reversal process can take anywhere from 1,000 to several thousand years. During that time, Earth's protection from solar wind and cosmic rays is reduced. Aurora might appear at all latitudes. Compass navigation would become unreliable, then impossible. Modern technology, from GPS satellites to power grids, could be affected. Should we be worried? Probably not immediately. Magnetic reversals have happened throughout Earth's history, and life survived them all. The last one occurred about 780,000 years ago, and Homo heidelbergensis, our ancestors, were around at the time. They made it through fine. But our modern technological civilization is far more dependent on the magnetic field than Stone Age humans were. A reversal would be disruptive, costly, potentially devastating for satellites and power infrastructure. It's one of those long-term, low-probability but high-impact scenarios we should be thinking about. Let's venture back into deep space, to one of the most extreme environments imaginable, the photon sphere of a black hole. This is a region, not at the event horizon but just outside it, where gravity is so strong that photons, particles of light, can orbit the black hole. Think about that. Light, which normally travels in straight lines, at least from its own perspective, is bent so severely by the black hole's gravity that it goes in circles. If you could somehow stand at the photon sphere, and again, I cannot emphasize enough that you could not actually survive this, you would see something extraordinary. You would see the back of your own head. Light from the back of your head would orbit around the black hole and come back to your eyes from the front. You'd be surrounded by multiple images of yourself, each one representing light that has orbited the black hole a different number of times before reaching you. The photon sphere for a non-rotating black hole exists at precisely 1.5 times the Schwarzschild radius, which is itself the radius of the event horizon. For a black hole the mass of the Sun, that's about 4.5 kilometers from the center. For the supermassive black hole at the center of M87, the one we imaged, the photon sphere is about 20 billion kilometers in radius, larger than the orbit of Neptune. When we look at that famous image of M87's black hole, what we're seeing is emission from the accretion disk, but that emission has been gravitationally lensed, bent by the black hole's gravity. Some of the light we're seeing has actually orbited the black hole before reaching us. The bright ring in the image is the photon sphere, or more precisely, it's the lensed image of the hot gas orbiting just outside the event horizon, with the brightness enhanced by photons that have orbited the black hole. Inside the photon sphere but outside the event horizon is the ergosphere, at least for rotating black holes. The ergosphere is a region where space-time itself is being dragged around by the black hole's rotation. You can't stand still in the ergosphere. It's impossible. Space-time is moving, and you're moving with it, dragged along like a leaf in a whirlpool. You can still escape from the ergosphere, unlike the event horizon. But you can't not rotate. The black hole forces you to orbit it. And here's where it gets really interesting. There's a process called the Penrose process, named after physicist Roger Penrose, where you can actually extract energy from a rotating black hole using the ergosphere. If you drop an object into the ergosphere and split it at just the right moment, one piece can fall into the event horizon while the other piece escapes, carrying more energy than the original object had. You're stealing rotational energy from the black hole itself, slowing it down infinitesimally while gaining energy. Some astrophysicists think the jets we see shooting out of black holes might be powered, at least in part, by the Penrose process. The magnetic fields threading the accretion disk tap into the rotational energy of the black hole, extracting power and channeling it into the jets. A supermassive black hole could power a galaxy's worth of activity just by giving up some of its spin. Now let's talk about something called the Great Attractor. About 150 to 250 million light-years away from us, in the direction of the constellations Triangulum Austral and Norma, there's something massive. Really massive. We can't see it directly because it's hidden behind the plane of the Milky Way, obscured by dust and gas and billions of stars in our own galaxy. But we can see its effect. Our galaxy, the Andromeda Galaxy, and thousands of other galaxies in our local region of space are all moving toward it, being pulled by its gravity at about 600 kilometers per second. What is it? Initially, astronomers thought it might be a supercluster of galaxies, a concentration of mass large enough to gravitationally attract everything around it. But as our observations improved, we realized the Great Attractor is itself part of something even larger. It's part of the Laniakea supercluster, a vast structure containing about 100,000 galaxies, including our own Milky Way. The name Laniakea comes from Hawaiian, meaning immeasurable heaven, which seems appropriate. The Laniakea supercluster isn't held together by its own gravity. It's too spread out for that. The expansion of the universe, driven by dark energy, is pulling it apart. But on smaller scales, within the supercluster, galaxies are gravitationally bound into smaller groups and clusters, and those groups are moving toward regions of higher density. The Great Attractor is one such region, though we now know it's not the center of Laniakea. That honor goes to an even larger structure called the Shapley supercluster, even further away. What fascinates me about this is the realization that we're not just rotating around the center of our galaxy. We're not just moving toward Andromeda on a collision course that will see our galaxies merge in about 4 billion years. We're also being pulled, along with thousands of other galaxies, toward a massive concentration of matter we can't even see clearly. Our motion through space is influenced by structures so large they challenge our understanding of cosmology. And speaking of large structures, let's talk about the Boötes Void, also called the Great Nothing. It's a vast, roughly spherical region of space, about 330 million light-years in diameter, that contains very few galaxies. In a region of space that should contain about 2,000 galaxies, the Boötes Void has only about 60. It's not completely empty, but it's eerily vacant compared to the surrounding regions. Voids are actually common in the large-scale structure of the universe. When we map the positions of galaxies on the largest scales, we see that they're not randomly distributed. They form filaments and sheets surrounding vast empty voids. The universe looks like a foam, with galaxies concentrated on the surfaces of bubbles and voids making up the interior. This structure emerged from tiny quantum fluctuations in the early universe, amplified by billions of years of gravitational evolution. But the Boötes Void is special because it's so big and so empty. When it was discovered in 1981, it challenged our understanding of how cosmic structure forms. How do you create a void that large? The answer lies in the initial conditions of the universe. Some regions started out slightly less dense than average. As denser regions attracted more matter through gravity, the less dense regions lost matter. The rich got richer, the poor got poorer. Over billions of years, this process created the filamentary structure we see today, with dense walls of galaxies surrounding empty voids. If you lived in a galaxy inside the Boötes void, your view of the universe would be strange. The night sky would be darker. Fewer galaxies would be visible. You'd have to look far to the edges of the void to see concentrations of galaxies. You might think you lived in a special place, in a universe that was emptier, lonelier than it really is. You'd be right in a sense. Your local neighborhood would be abnormally empty. But on even larger scales, beyond the void, the universe would reveal itself to be just as full of galaxies as anywhere else. Let's discuss something that's happening right now all around us, that we experience every day but rarely think about: time dilation. According to Einstein's theory of relativity, time is not absolute. It flows at different rates depending on your motion and the strength of the gravitational field you're in. The faster you move, the slower your clock ticks relative to someone at rest. The deeper you are in a gravitational well, the slower time passes relative to someone further away. This isn't speculation. This is measured fact. GPS satellites orbit about 20,000 kilometers above Earth's surface. At that altitude, Earth's gravity is weaker than at the surface, so time runs faster for the satellites, about 45 microseconds per day faster. But the satellites are also moving at about 14,000 kilometers per hour, and that motion causes time to run slower, about 7 microseconds per day slower. The net effect is that clocks on GPS satellites run about 38 microseconds per day faster than clocks on the ground. That doesn't sound like much, but light travels about 300 meters in a microsecond. If we didn't correct for relativistic effects, GPS would accumulate errors of about 10 kilometers per day. Within weeks, it would be useless. Every time you use GPS to navigate, you're relying on Einstein's relativity being correct. But let's take this to extremes. Near a black hole, time dilation becomes dramatic. If you watched a clock falling toward a black hole's event horizon, you'd see it tick slower and slower as it got closer. At the event horizon, time would appear to stop completely from your perspective. You'd never actually see the clock cross the horizon. You'd see it get closer and closer, redder and redder as the light gets stretched by gravity, and eventually fade from view, frozen in time at the edge of the black hole. But from the clock's perspective, nothing special happens at the event horizon. Time continues normally. The clock crosses the horizon and falls toward the singularity. It's only to outside observers that time appears to stop. This is one of the most counterintuitive aspects of relativity. There's no single universal now. Different observers can disagree about what events are simultaneous, about what's happening now versus what happened in the past or future. Near a supermassive black hole like the one at the center of M87, you could, in principle, orbit just outside the event horizon, experiencing extreme time dilation. An hour for you might be years or decades for someone far from the black hole. You could watch the universe age, see stars being born and dying, watch galaxies evolve, all in fast forward while you experience only a brief time. You'd be a time traveler, moving into the future without any way to return to the past. This isn't science fiction. This is what Einstein's equations tell us. Time is relative. It's flexible. It depends on where you are and how fast you're moving. And on cosmic scales, near extreme gravity or at relativistic speeds, these effects become impossible to ignore. Let me tell you about rogue planets. These are planets that don't orbit any star. They wander through the galaxy alone, untethered, drifting in the darkness of interstellar space. We've detected a few dozen of them, though we suspect there might be trillions of them in our galaxy alone, possibly outnumbering stars. How do planets become rogues? Most likely, they formed around stars in the normal way but were then ejected. Maybe a close encounter with another planet destabilized the orbit. Maybe the star system was part of a binary that broke apart. Maybe a passing star perturbed the young planetary system. Whatever the mechanism, the planet was flung into interstellar space, destined to wander alone, perhaps forever. What's a rogue planet like? Cold, unimaginably cold. With no star to warm it, temperatures would be just a few degrees above absolute zero, maybe 20 or 30 Kelvin. The surface would be covered in exotic ices, frozen hydrogen, nitrogen, oxygen. Any atmosphere would have long since condensed and fallen to the surface as snow. The planet would be completely dark, lit only by the faint glow of distant stars. But here's something interesting. A rogue planet might still have a molten interior. Radioactive decay inside the planet could generate heat for billions of years. Tidal heating from moons could add more energy. A large enough rogue planet could maintain a subsurface ocean beneath a thick ice shell, similar to what we think exists on Europa or Enceladus. Could life exist in such an ocean? It's possible. Life doesn't need sunlight. It just needs liquid water, energy, and the right chemistry. Hydrothermal vents on the ocean floor of a rogue planet could provide both energy and nutrients. Life on a rogue planet would never see a star. It would never experience day or night, seasons, any cycle related to stellar orbit. Its entire existence would be in darkness, lit only by the faint glow of geothermal vents. If that life ever evolved intelligence, what would its science look like? Would it even conceive of stars? Would it understand the vastness of the universe? Or would it think its ocean was all that existed? Now let's talk about zombie stars, type Ia X supernovae. These are thermonuclear explosions like type Ia supernovae, caused when a white dwarf star accretes matter from a companion and reaches a critical mass. But while a normal type Ia supernova completely destroys the white dwarf, leaving nothing behind, a type Ia X supernova is weaker. It blows off the accreted material and may be part of the white dwarf's outer layers, but the core survives. The white dwarf doesn't die. It survives its own supernova. It's a zombie star, technically dead, in that it's not fusing elements in its core anymore. It's a white dwarf, but refusing to stay dead. And the remarkable thing is, this process can repeat. The white dwarf can accrete more material, detonate again, survive again. It's a star that explodes over and over, each time throwing off matter and energy, each time refusing to be completely destroyed. We've found evidence of multiple eruptions from some white dwarf systems. SN 1991T, for instance, shows signs of previous explosions. The star that became SN 1991T had probably exploded before, survived, and then exploded again when we happened to be watching. There might be white dwarfs in our galaxy right now that have exploded dozens of times over billions of years, each time blowing off their outer layers, each time surviving to accrete more matter and do it all over again. This has implications for our understanding of type Ia supernovae, which we use as standard candles to measure cosmic distances. If some fraction of type Ia supernovae come from these zombie stars, from white dwarfs that have already exploded before, their properties might be different from supernovae caused by first-time exploding white dwarfs. This could affect our measurements of the expansion of the universe, our understanding of dark energy, everything that depends on type Ia supernovae being standardizable. The universe is full of surprises. Just when we think we understand something, nature reveals another layer of complexity. Let's talk about the bullet cluster. This is actually two galaxy clusters, each containing hundreds of galaxies, that collided with each other. When galaxy clusters collide, and yes, this happens, the galaxies themselves mostly pass through each other. Space is so vast and galaxies so small, relatively speaking, that direct collisions between individual stars are incredibly rare. But the hot gas that fills the space between galaxies, the intracluster medium, doesn't pass through. Collides, heats up, slows down. When we look at the bullet cluster, we see exactly this. The galaxies have passed through each other and are now separating on the far side of the collision. But the hot gas, visible in X-ray images, has stayed behind, piled up where the two clusters collided. It's a cosmic train wreck, frozen in time. Well, frozen from our perspective, the collision is ongoing and will take millions of years to complete. But here's the fascinating part. When we measure where the mass is using gravitational lensing, we find that most of the mass isn't where the gas is. Most of the mass is where the galaxies are. In fact, the mass appears to have passed right through the collision, just like the galaxies did, unaffected by the gas piling up in the middle. This is direct evidence for dark matter. The dark matter halos surrounding each galaxy cluster pass through each other, just like the galaxies, because dark matter doesn't interact with normal matter, it doesn't collide, it doesn't slow down. It's only affected by gravity. So the dark matter kept going while the gas stayed behind. We can literally see the separation of normal matter and dark matter in the bullet cluster. This observation was a major blow to alternative theories of gravity that tried to explain galactic rotation curves without invoking dark matter. Those theories predicted that mass should be where the visible matter is, where the gas is. But that's not what we observe. The mass is where the galaxies are, where we can't see anything. Dark matter is real. It's not just a mathematical trick. It's actual substance, invisible but present, dominating the mass of galaxy clusters. Now let me take you to the strangest state of matter we know, quark-gluon plasma. For the first few microseconds after the Big Bang, the universe was too hot for protons and neutrons to exist. Temperatures were trillions of degrees. At those temperatures, protons and neutrons break apart into their constituent quarks and gluons, creating a soup of fundamental particles. This is quark-gluon plasma. We've recreated this state of matter on Earth in particle accelerators like the Relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN. By smashing heavy nuclei together at nearly the speed of light, we can create temperatures over 4 trillion degrees Celsius, hot enough to melt protons and neutrons. For a fraction of a second, in a space smaller than an atom, we recreate the conditions that existed in the infant universe. And quark-gluon plasma behaves strangely. It flows with almost no viscosity, less viscosity than liquid helium, making it the most perfect fluid ever observed. It's opaque to quarks, meaning quarks moving through it lose energy rapidly, as if they're moving through a thick liquid even though it has almost no viscosity. It's a liquid that acts like it's both impossibly thin and impossibly thick at the same time. This isn't just academic curiosity. Understanding quark-gluon plasma helps us understand the early universe, what happened in the first moments after the Big Bang, how matter as we know it came into existence. Every proton in your body, every neutron was once part of quark-gluon plasma. Studying this exotic state of matter is studying the origin of everything. And speaking of origins, let's talk about cosmic inflation. In the first fraction of a second after the Big Bang, approximately 10 to the minus 36 seconds after time began, the universe underwent a period of exponential expansion. Space itself expanded faster than the speed of light, doubling in size every 10 to the minus 35 seconds or so. In less time than it takes light to cross a proton, the universe expanded from smaller than an atom to larger than a grapefruit, maybe larger than a galaxy, maybe larger than anything we can observe today. This is inflation, and it solves several problems with the standard Big Bang model. It explains why the universe is so uniform, why the cosmic microwave background looks the same in all directions. If the universe inflated from a tiny region, that region had time to come to thermal equilibrium before inflating, and inflation stretched that uniformity across the entire observable universe. It explains why space is so flat, why the geometry of the universe appears Euclidean. Inflation stretches space like inflating a balloon, and any curvature gets smoothed out. But inflation also makes predictions. It predicts that quantum fluctuations in the inflating space would be stretched to cosmic scales, creating variations in density that would eventually grow into galaxies and galaxy clusters. And when we look at the cosmic microwave background, we see exactly those predicted fluctuations. The pattern of hot and cold spots in the CMB matches the predictions of inflation remarkably well. Inflation also predicts gravitational waves, ripples in spacetime created by the rapid expansion. These primordial gravitational waves would leave a distinct signature in the polarization of the cosmic microwave background. We haven't detected them yet, though experiments like BICEP and LIGHTBIRD are searching. Finding primordial gravitational waves would be the smoking gun evidence for inflation, proof that the universe really did undergo this period of exponential expansion. But here's the weird part. If inflation is correct, the observable universe, everything we can see or ever will be able to see, is just a tiny bubble in a much larger cosmos. Outside our bubble, space is still inflating and will continue to inflate forever. New bubble universes are constantly forming, each with potentially different physical constants, different laws of physics. We live in a multiverse, an infinite collection of bubble universes, each isolated from the others, each perhaps with unique properties. This is speculative, I want to be clear. We have no direct evidence of other bubble universes. We can't see beyond our cosmic horizon. But if inflation is correct, and the evidence suggests it is, then a multiverse is almost an inevitable consequence. The universe is not just stranger than we imagine. It might be stranger than we can imagine. Let's discuss something happening in our own cosmic backyard. The Andromeda Galaxy is going to collide with the Milky Way. In about 4 billion years, these two giant spiral galaxies will merge, creating a new, larger elliptical galaxy that astronomers have already nicknamed Milkomeda or Milkdromeda. This sounds catastrophic, and on a galactic scale it is. The collision will take hundreds of millions of years. The two galaxies will approach, pass through each other, their mutual gravity distorting their spiral arms, pulling out long tidal tails of stars. Then they'll fall back together, collide again, each collision scrambling their structures more. Eventually, after several passes, they'll settle down into a single elliptical galaxy, their spiral structures gone, destroyed by the violence of the merger. But for an individual star, for our sun, if it's still around in 4 billion years, which it will be, the collision will be largely uneventful. Galaxies are mostly empty space. The distances between stars are so vast that the probability of any individual star colliding with another star during the merger is astronomically small. The sun will be jostled, its orbit around the galactic center changed, possibly ejected from the galaxy entirely. But it won't hit anything. Earth won't be affected by the collision directly. Well, except for one thing. The sun will be dead in a different way by then. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. This will cause it to expand into a red giant, engulfing Mercury, Venus, and possibly Earth. If Earth survives, it will be a scorched cinder, completely uninhabitable. So while the galactic collision won't destroy Earth, the sun's natural evolution will. Life on Earth has perhaps another billion years, maybe less, before the increasing luminosity of the sun makes the planet uninhabitable. The oceans will evaporate. The atmosphere will be stripped away. Complex life will end. If humanity or whatever we evolve into wants to survive, we'll need to leave Earth long before the sun becomes a red giant. We'll need to become a spacefaring civilization, capable of building habitats far from our home star, perhaps journeying to other star systems entirely. The universe is telling us, in no uncertain terms, that our time on Earth is limited. Not in the span of human lifetimes, not even in the span of recorded history, but on cosmic timescales, Earth's habitability is temporary. We're living on a planet with an expiration date, orbiting a star with an expiration date, in a galaxy that's going to collide with another galaxy. Everything is temporary. Everything changes. Permanence is an illusion. Now let's discuss something that challenges our understanding of causality itself: quantum entanglement. When two particles are entangled, measuring the properties of one particle instantly affects the other, no matter how far apart they are. If you measure an entangled electron spin and find it's up, you instantly know its partner's spin is down, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But experiment after experiment has confirmed that entanglement is real. Particles really do influence each other instantaneously across vast distances. Information doesn't travel between them. You can't use entanglement to send messages faster than light. But the correlation is real and instantaneous. What does this mean? It means the universe is more connected than we thought. It means the idea of locality, that objects are only influenced by their immediate surroundings, is wrong at a fundamental level. Entangled particles behave as a single quantum system, even when separated by billions of light years. The particles aren't sending signals to each other. They're not communicating. They're simply not separate in the way we intuitively think they should be. Some physicists interpret this as meaning the universe is fundamentally non-local, that at a quantum level, everything is connected to everything else. Others interpret it as meaning we don't fully understand what we mean by separate. Maybe separation is an illusion, an artifact of how we perceive reality rather than a fundamental feature of it. And here's where it gets really strange. The universe produces entangled particles constantly. When stars explode, when particles collide in space, they create entangled pairs that fly off in opposite directions. Right now, you're probably being hit by entangled photons from distant astronomical sources. Does this mean you're entangled with those sources? In a sense, yes, though the entanglement is incredibly delicate and destroyed almost immediately by interactions with the environment. But for a brief moment, you're quantum mechanically connected to distant parts of the universe. Let me tell you about the coldest place in the universe. It's not in deep space, despite the common misconception. The cosmic microwave background, the leftover radiation from the Big Bang, gives all of space a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. You can't get colder than that in empty space, but you can get colder in the laboratory. The Boomerang Nebula, a dying star about 5,000 light-years away, has a temperature of about 1 Kelvin, colder than the cosmic microwave background. How? The star is expelling gas at high speeds, and that expanding gas cools, just like air rushing out of a compressed air canister gets cold. The Boomerang Nebula is essentially a giant cosmic refrigerator, cooling itself by expansion. But we've done better on Earth. In laboratories around the world, physicists have cooled atoms to within a billionth of a degree above absolute zero, temperatures where quantum effects become visible on macroscopic scales. At these temperatures, atoms slow down so much that their quantum wave nature becomes apparent. They stop behaving like particles and start behaving like waves. Multiple atoms can occupy the same quantum state, creating what's called a Bose-Einstein condensate, a state of matter where thousands or millions of atoms act as a single quantum object. In a Bose-Einstein condensate, weird things happen. Light can be slowed to a crawl just 17 meters per second, slower than a bicycle. Individual atoms become indistinguishable, losing their identity as separate particles. Quantum interference patterns appear in the condensate's density, proof that matter really is a wave at a fundamental level. Why do we care? Because studying matter at these extreme temperatures teaches us about quantum mechanics, about how the universe works at its most fundamental level. And there are practical applications too. Quantum computers might use Bose-Einstein condensates to perform calculations impossible for classical computers. Ultra-precise atomic clocks use similar cooling techniques to measure time with incredible accuracy. Understanding the quantum world isn't just academic curiosity. It's the foundation of future technology. Let's talk about something that's happening right now all around us that we're completely oblivious to: neutrino flux. Neutrinos are ghostly particles that barely interact with normal matter. They're created in nuclear reactions, in the sun's core, in supernova explosions, in Earth's interior, even in your own body from radioactive decay. And they pass through everything. Right now, billions of neutrinos from the sun are passing through your body every second. They entered through the top of your head, or through your feet if the sun is below the horizon, and they exited out the other side. You didn't feel a thing. A neutrino could pass through a light year of solid lead and probably not interact with a single atom. To a neutrino, matter is essentially transparent. The entire Earth is like fog to a neutrino. It barely notices we're here. We've built detectors to catch neutrinos, enormous tanks of ultrapure water or other materials buried deep underground to shield from cosmic rays. And very occasionally, maybe once a day in a detector containing thousands of tons of material, a neutrino will interact with an atom, producing a tiny flash of light that we can detect. From those rare interactions, we learn about the sun, about supernovae, about the early universe. In 1987, before visible light from supernova 1987A reached Earth, neutrinos from the explosion were detected by underground detectors in Japan and Ohio. The neutrinos, traveling at nearly the speed of light and unimpeded by the outer layers of the exploding star, reached Earth hours before the light, which had to work its way out through the debris of the explosion. For a brief time, we knew a star had exploded. We detected its death cry before we could see it with our eyes. Neutrinos are messengers from the heart of the cosmos, carrying information from places light can never escape, from the cores of stars, from the centers of supernovae, from near the event horizons of black holes. If we could see in neutrinos instead of light, the universe would look completely different. The sun wouldn't have a surface. We'd see its core directly, watching nuclear fusion reactions in real time. Supernovae would appear hours before the optical explosion. The cosmic neutrino background, leftover neutrinos from the Big Bang itself, would fill the sky. We're building better neutrino detectors, larger, more sensitive, deployed in oceans and under ice. We're learning to see the universe through neutrino eyes. And what we're discovering is that there's a whole invisible universe out there, carrying energy and information through space, interacting with matter so rarely that we barely notice it's there, but present in such vast numbers that neutrinos actually outweigh all the stars combined. Let me tell you about Hawking radiation, a phenomenon so subtle we've never directly observed it, yet so profound it reveals deep connections between gravity, quantum mechanics, and thermodynamics. Stephen Hawking showed, through theoretical calculations, that black holes aren't truly black. They emit radiation very slowly, very faintly, gradually losing mass over immense timescales. Here's how it works. Quantum mechanics tells us that empty space isn't really empty. It's filled with virtual particles, particle-antiparticle pairs that pop into existence and immediately annihilate, living only for the briefest instant allowed by Heisenberg's uncertainty principle. Normally, this has no observable effect. The particles appear and disappear so quickly they're fundamentally undetectable. But near a black hole's event horizon, something different can happen. A particle-antiparticle pair appears, and before they can annihilate, one falls past the event horizon while the other escapes. From an outside observer's perspective, the black hole has emitted a particle. It has radiated energy, and since energy is equivalent to mass, the black hole has lost mass. This is Hawking radiation, and it's incredibly faint. A black hole the mass of the sun would emit Hawking radiation at a temperature of about 60 billionths of a Kelvin. That's much colder than the cosmic microwave background. The black hole is absorbing more radiation from the universe than it's emitting through Hawking radiation. It's growing, not shrinking. But for small black holes, Hawking radiation becomes significant. A black hole with the mass of a mountain would be about the size of an atom and would glow white-hot, emitting tremendous amounts of radiation and evaporating in a flash. Unfortunately, or perhaps fortunately, we don't think black holes this small exist naturally. The universe never produced conditions extreme enough to create them. But over incomprehensibly long timescales, over gugals of years, even stellar mass black holes will eventually evaporate through Hawking radiation. After the last stars have burned out, after all the white dwarfs have cooled to black dwarfs, after the universe has become a dark, cold, empty place, black holes will remain. And slowly, infinitesimally slowly, they'll evaporate until eventually, in the far future, they'll explode in a final burst of radiation and be gone. The universe won't be empty forever. Even black holes are temporary. Given enough time, everything ends. Even the most permanent seeming structures in the cosmos are just long-lived, not eternal. Let's discuss something happening in our galaxy right now. Star formation, the process by which cold gas clouds collapse under their own gravity to birth new stars. In molecular clouds, vast regions of space filled with hydrogen, helium, and trace amounts of heavier elements, gravity slowly wins. Local overdensities attract more material. The cloud fragments. Dense cores form. As material falls inward, It heats up through gravitational contraction. Eventually, the center becomes hot and dense enough for nuclear fusion to ignite. A star is born, but not all at once. The process takes millions of years for a sun-like star, hundreds of thousands of years for more massive stars. And it's messy. Matter doesn't fall straight inward. It carries angular momentum, so it forms a disk around the forming star, an accretion disk. Some of that material continues falling onto the star. Some of it is blown away by stellar winds, and some of it, crucially, coalesces into planets. We've seen this process with our own telescopes. Images from ALMA, the Atacama Large Millimeter Array, show young stars surrounded by disks of gas and dust. We can see gaps in those disks where planets are forming, clearing out their orbits. We can see spiral patterns in the disks, signatures of gravitational interactions between the forming planets and the disk material. We're watching planetary systems being born, and every star forms with a disk, every single one, which means planet formation is probably the rule, not the exception. The Kepler Space Telescope showed us that most stars have planets. The galaxy is teeming with them. Billions of planets. Trillions, probably. Rocky planets, gas giants, ice worlds, things we don't even have categories for. Some of those planets are in their star's habitable zone, the region where temperatures are right for liquid water to exist on the surface. Earth is in our sun's habitable zone. We know of thousands of exoplanets, several dozen in their respective habitable zones. How many of them have life? We don't know. We're just now developing the technology to analyze exoplanet atmospheres, looking for biosignatures, gases that might indicate biological activity. But here's something to consider. We're discovering planets not just around sun-like stars, but around red dwarfs, small cool stars that are by far the most common type in the galaxy. Red dwarfs live for trillions of years, plenty of time for life to evolve, if it can get started at all. Some of these red dwarfs have planets. Proxima Centauri, the nearest star to our sun, has at least 2 planets, one potentially in the habitable zone. If life exists on a planet around a red dwarf, what would it be like? The star would appear huge in the sky, much larger than our sun, but dimmer, redder. The habitable zone is close to the star, so planets there are probably tidally locked, one side always facing the star, eternally day, the other side always dark, eternally night. Life, if it exists, might be confined to the twilight zone, the band around the planet where day meets night. But maybe life could adapt. Maybe oceans or atmospheres could transport heat from the day side to the night side, making more of the planet habitable. Maybe life could evolve to live in the eternal day or the eternal night. Life on Earth has adapted to every environment imaginable, from boiling hydrothermal vents to frozen Antarctic deserts to miles underground to the stratosphere. Why not eternal day or eternal night? We're on the verge of answering one of humanity's oldest questions. Are we alone? In the next few decades, as our telescopes and instruments improve, we'll analyze the atmospheres of dozens, maybe hundreds of potentially habitable worlds. If we detect oxygen and methane together, gases that don't naturally coexist without being constantly replenished, that might be evidence of life. Not proof, but strong evidence. And then we'll know. We'll know that life isn't unique to Earth, that the universe is alive. Let me tell you about cosmic rays, and no, they're not rays. They're particles, mostly protons, accelerated to nearly the speed of light by some of the most violent processes in the universe. They zip through space, these atomic bullets, carrying energies that would make our most powerful particle accelerators look like toys. And they hit Earth all the time, billions of them every second. Most cosmic rays are relatively low energy and are deflected or absorbed by Earth's magnetic field and atmosphere. They create showers of secondary particles when they hit atmospheric atoms, and those secondary particles are what we detect at ground level. But some cosmic rays, the ultra-high energy ones, carry so much energy that they punch through everything. We're talking about protons with the kinetic energy of a baseball. A single proton, with the energy of a baseball. Let that sink in. Where does that energy come from? We don't know for sure. Supernova remnants accelerate particles, probably accounting for most cosmic rays up to a certain energy. But the ultra-high energy cosmic rays, the ones with truly mind-boggling energies, must come from something even more extreme. Active galactic nuclei, maybe those jets shooting out of supermassive black holes, or gamma ray bursts, the most luminous explosions in the universe. Or maybe something we haven't thought of yet. And here's the really strange part. There's a cutoff. Above a certain energy, we don't detect cosmic rays at all, or at least they're extraordinarily rare. This is called the GZK cutoff after the physicists who predicted it. The idea is that ultra-high energy protons interact with the cosmic microwave background, the leftover light from the Big Bang that permeates all of space. Those interactions sap energy from the protons, limiting how far they can travel. Ultra-high energy cosmic rays can't come from more than about 50 million light-years away, or they'll lose too much energy interacting with the CMB. So when we detect an ultra-high energy cosmic ray, it must have originated relatively nearby, within our local supercluster of galaxies. That's still an enormous volume of space, but it's a start. We can look for candidate sources, nearby galaxies with active galactic nuclei, recent supernovae, anything that might produce particles with such absurd energies. And we're building detectors to catch more of them. The Pierre Auger Observatory in Argentina covers 3,000 square kilometers, watching for the air showers created when cosmic rays hit the atmosphere. Every time an ultra-high energy cosmic ray is detected, we're seeing evidence of the most powerful particle accelerators in the universe, natural machines that make our technology look primitive by comparison. Now let's talk about something I find deeply philosophical. The observable universe has a boundary. Not a physical edge, not a wall or barrier, but a horizon beyond which we cannot see, no matter how good our telescopes become. This is the cosmological horizon, and it exists because the universe has a finite age and light has a finite speed. The Big Bang happened 13.8 billion years ago. Light from objects more than 13.8 billion light-years away hasn't had time to reach us yet. That light is still on its way, traveling through the expanding cosmos, and it will eventually get here. But right now, there's a spherical region around Earth about 93 billion light-years in diameter, taking into account the expansion of space, that represents everything we can possibly see. Beyond that horizon, galaxies exist. We know they do because the universe is, as far as we can tell, roughly the same everywhere. But we can't see them. Their light hasn't reached us yet. And due to the accelerating expansion of the universe, driven by dark energy, some of that light will never reach us. Galaxies beyond a certain distance are being carried away by the expansion of space faster than light can make up the distance. They're slipping beyond our horizon, permanently, disappearing from view not because they've been destroyed but simply because the space between us and them is expanding too quickly. This means that our descendants, billions of years from now, if humanity survives that long, will live in a lonelier universe. Fewer galaxies will be visible. The night sky will be darker. Measurements that we can make today, observations of distant galaxies that tell us about the expansion of the universe, will be impossible in the far future because those galaxies will have slipped beyond the horizon. Future civilizations might not even know that the universe is expanding unless they have records from our era. And here's the humbling part. There's no reason to think our observable universe is special. Beyond our horizon, the universe keeps going. There are galaxies we'll never see, stars that will never be observed by human eyes or human instruments, planets that will remain forever unknown to us, possibly civilizations, intelligences, minds pondering the cosmos just as we are, completely isolated from us by the vast distances and the expansion of space. We think of the universe as everything, but really we have access to only a tiny bubble, a region determined by the speed of light and the age of the universe. The true universe, the entire cosmos, is almost certainly much larger than what we can observe. How much larger? We don't know. Maybe infinitely larger. Maybe it goes on forever. Or maybe it curves back on itself, finite but unbounded, like the surface of a sphere. We don't know, And unless the curvature is very close to our horizon, we may never know. Let me tell you about one of the most spectacular phenomena in the universe: gamma ray bursts. These are brief flashes of the highest energy light, gamma rays, that appear randomly in the sky, last for a few seconds to a few minutes, and then fade away. For that brief time, a gamma ray burst is the brightest source of gamma rays in the entire universe, outshining everything else combined. We detect about 1 gamma ray burst per day somewhere in the sky, and we now understand that they come in 2 flavors: short bursts, lasting less than 2 seconds, and long bursts, lasting more than 2 seconds. They have different causes. Short gamma ray bursts are produced by colliding neutron stars, the same events that create kilonovae and heavy elements. Long gamma ray bursts are produced by collapsing massive stars, hypernovae, stars so massive and so energetic that when they collapse, they don't just form a neutron star or a black hole, they explode in a catastrophic fireball. Both types involve similar mechanisms: matter falling onto a newly formed black hole, creating jets of gamma rays that shoot out along the rotation axis at nearly the speed of light. If one of those jets happens to be aimed at Earth, we see a gamma ray burst. If it's aimed somewhere else, we might miss it entirely, even though the explosion is just as powerful. Gamma ray bursts are dangerous. If one occurred in our galaxy within a few thousand light-years of Earth, and its jet was aimed at us, it could damage or destroy our ozone layer, exposing life on Earth to harmful ultraviolet radiation. Mass extinctions in Earth's history might have been caused by nearby gamma ray bursts, though this is speculative. The good news is that gamma ray bursts are rare, and the probability of one occurring close enough and aimed at us is very small. But they do occur. Somewhere in the universe, right now, a massive star is dying, collapsing, forming a black hole, launching jets of gamma rays into space. Those gamma rays are traveling through the cosmos, and in a few billion years, they'll reach Earth. But by then, they'll be spread out, diluted, harmless. We'll detect them as just another distant gamma ray burst, unaware of the devastation they might have caused to any unfortunate worlds in their path. Let's talk about cosmic strings. These are hypothetical one-dimensional topological defects in spacetime, relics from the early universe when different regions of space underwent phase transitions at different times, like how cracks can form in ice when water freezes unevenly. If they exist, and that's a big if, cosmic strings would be incredibly thin, much thinner than an atom, but incredibly massive. A light-year-long piece of cosmic string could have the mass of a galaxy. A cosmic string would warp space around it. Anything passing on one side would be gravitationally lensed differently than anything passing on the other side. If a cosmic string passed through the solar system, and again, this is purely hypothetical, it could disrupt planetary orbits or even cut through planets like a wire through cheese, though the probability of this is essentially zero. We've looked for cosmic strings. We've searched for their gravitational signatures, for the way they would lens distant galaxies. So far, we've found nothing. But that doesn't mean they don't exist. If cosmic strings are rare, or if they're located far outside our observable universe, we wouldn't see them. They remain a prediction of some theories, an exotic possibility lurking in the mathematical foundations of physics, waiting to be discovered or ruled out. The universe might be threaded with these invisible strings, a cosmic web of one-dimensional objects, each carrying the energy of countless stars, remnants of a phase transition that occurred in the first moments after the Big Bang. Or they might not exist at all. That's the frustrating beauty of theoretical physics. Sometimes we predict things that turn out to be real. Sometimes we predict things that the universe decided not to include. We won't know until we look. Now let's discuss gravitational waves in more detail because they're fascinating and they've revolutionized astronomy. In 2015, LIGO detected the first gravitational waves from 2 colliding black holes. That detection, announced in 2016, confirmed a century-old prediction by Einstein and opened a new window on the universe. Gravitational waves are ripples in spacetime itself. When massive objects accelerate, they create these ripples which travel outward at the speed of light. Usually, the ripples are tiny, undetectable. But when truly massive objects, like black holes or neutron stars, spiral together and merge, The gravitational waves they produce are strong enough to detect, even from billions of light years away. LIGO works by measuring changes in distance smaller than 1,000th the diameter of a proton. That's not a typo. It uses laser interferometry, splitting a laser beam and sending the two halves down perpendicular arms several kilometers long, then recombining them. Normally, the beams cancel out perfectly, but when a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction. The lengths of the arms change, and the laser beams no longer cancel perfectly. That tiny difference, that absurdly small change in the interference pattern, tells us a gravitational wave passed by. Since that first detection, we've detected dozens of gravitational wave events, black hole mergers, neutron star mergers, maybe even black holes merging with neutron stars. Each detection tells us something about these events, the masses of the objects involved, how fast they were spinning, how far away they were. But the really exciting possibility is that gravitational wave astronomy will let us see events that are invisible in electromagnetic radiation. Two black holes merging don't emit light, at least not directly. We can't see them with any telescope, but they scream in gravitational waves. Gravitational wave detectors let us observe the universe in an entirely new way, detecting phenomena that were always invisible before. And we're building more sensitive detectors. LISA, the Laser Interferometer Space Antenna, will be launched in the 2030s, a space-based gravitational wave detector with arms millions of kilometers long. It will detect lower-frequency gravitational waves from supermassive black hole mergers, events so energetic they dwarf anything LIGO can detect. We're at the beginning of gravitational wave astronomy. In a few decades, we'll have a catalog of thousands of events. We'll map the population of black holes and neutron stars across the universe. We'll watch supermassive black holes at the centers of galaxies merge when their host galaxies collide. We'll maybe even detect the gravitational wave background from the early universe, ripples created by inflation itself. The universe is talking to us in a new language, and we're finally learning to listen. Let me take you to one of the most extreme environments in the solar system, the surface of Venus. With a temperature of about 460 degrees Celsius, hot enough to melt lead, and an atmospheric pressure 90 times that of Earth, equivalent to being a kilometer underwater, Venus is a hellscape. The atmosphere is almost entirely carbon dioxide, with clouds of sulfuric acid. The surface is perpetually shrouded in these thick clouds, blocking any view of the sky. If you could stand on Venus, which you absolutely could not survive, you wouldn't see the sun. You'd see a dim, reddish glow diffusing through the clouds, never changing, never moving. Venus wasn't always like this. We think Venus and Earth formed with similar amounts of water. But Venus is closer to the sun, and that made all the difference. Water in Venus's atmosphere absorbed infrared radiation from the surface, creating a runaway greenhouse effect. As temperatures rose, more water evaporated. More water in the atmosphere meant more heat trapped. Temperatures rose further. Eventually, the oceans boiled away completely. Water vapor in the upper atmosphere was broken apart by ultraviolet radiation from the sun, the hydrogen escaped to space, and Venus lost its water permanently. Today, Venus is a cautionary tale, a demonstration of what runaway greenhouse effects can do to a planet. And it's relevant because we're adding greenhouse gases to Earth's atmosphere at an unprecedented rate. We're not going to turn Earth into Venus. Let me be clear. We don't have enough fossil fuels to create a thick carbon dioxide atmosphere like Venus. But we can make Earth significantly warmer, enough to disrupt weather patterns, raise sea levels, threaten ecosystems and agriculture. Venus reminds us that planets can change dramatically. Conditions that seem stable, that have been stable for billions of years, can shift. Venus was probably habitable once in its early history, before the greenhouse effect spiraled out of control. Now it's the hottest planet in the solar system, hotter even than Mercury, which is closer to the sun. That transformation took millions of years on Venus. But the lesson is clear: atmospheres matter, climate matters, and changes can be irreversible. Now let's talk about Titan, Saturn's largest moon, and one of the most fascinating worlds in the solar system. Titan has a thick atmosphere, thicker than Earth's, composed mostly of nitrogen with a trace of methane. The atmospheric pressure at Titan's surface is about 50% higher than Earth's. And Titan has weather. Methane rain falls from the sky. Methane rivers flow across the surface. Methane lakes and seas fill basins in Titan's high latitudes. It's Earth-like in structure, but with methane filling the role that water plays on Earth. The Cassini-Huygens mission gave us our first close-up look at Titan. The Huygens probe landed on the surface in 2005, returning images of a landscape sculpted by liquid. Rounded pebbles on the shoreline of a dried-up lake. River channels meandering across plains. Mountains rising from the surface. It looked in many ways like Earth, just much colder. Titan's surface temperature is about minus 180 degrees Celsius. Water ice is as hard as rock. Methane is a liquid. Titan has an active weather cycle. Methane evaporates from the surface, rises into the atmosphere, condenses into clouds, and falls as rain. The rain erodes the surface, carving valleys and canyons, filling lakes. Some lakes are permanent. Some are seasonal, filling during Titan's spring and evaporating in summer. Titan has seasons, caused by Saturn's tilt as it orbits the Sun. A year on Titan is nearly 30 Earth years, so seasons last about 7 years each. And Titan might have life, not on the surface where conditions are too harsh, but underground. Beneath the icy crust, we think Titan has a subsurface ocean of liquid water, kept warm by tidal heating from Saturn. That ocean could be habitable. It has liquid water, energy from tidal flexing, and complex organic chemistry. Cassini detected hydrogen molecules outgassing from Titan's atmosphere, which some scientists interpret as a possible signature of methanogenesis, life producing methane. We don't know if life exists on Titan, but it's one of the most promising places to look in the solar system. NASA is planning to send a drone called Dragonfly to Titan in the 2030s. It will fly through Titan's thick atmosphere, landing at multiple sites, analyzing the chemistry, searching for signs of life. Titan might be our best chance of finding extraterrestrial life in our own solar system. Let's discuss something that's surprisingly common in the universe: rogue moons. Just like planets can be ejected from their star systems, moons can be ejected from their planets. A close encounter with another planet, a passing star, a supernova shockwave, any number of events could tear a moon away from its planet and send it wandering through space. Some of these rogue moons might still have atmospheres, especially if they started out large, like Titan. A Titan-sized rogue moon, wandering through interstellar space, would be incredibly cold on its surface. But its subsurface ocean, if it had one, might persist for millions or even billions of years, heated by radioactive decay in the moon's core. Life that evolved in that ocean when the moon still orbited its planet might continue living, unaware that its world had been cast into the cosmic wilderness. This is speculative, of course. We haven't detected any rogue moons outside our solar system, but statistically they should exist. Planets are common. Moons are common around planets. Some fraction of moons must be ejected over time. The galaxy might contain billions of rogue moons, wandering alone, forever separated from the planets they once orbited. And if some of those moons harbor life, trapped in subsurface oceans, those biospheres would be completely isolated. They could never leave their ocean. They could never see stars. They wouldn't even know stars existed. Their entire universe would be the water and ice of their moon. If intelligence evolved in such an environment, what would its science look like? What kind of cosmology would it develop without any view of the cosmos? Now let's talk about the cosmic web, the large-scale structure of the universe. When we map the positions of galaxies across vast volumes of space, we see they're not randomly distributed. They form filaments, long strands of galaxies connecting massive clusters, with vast voids in between. The universe looks like a foam or sponge, with structure on scales of hundreds of millions of light-years. This structure formed from tiny quantum fluctuations in the very early universe, amplified by billions of years of gravitational evolution. Regions that started out slightly denser attracted more matter, becoming denser still. Regions that started slightly less dense lost matter to their denser neighbors. Over time, this created the filamentary structure we see today. Galaxy clusters sit at the nodes of the cosmic web, where filaments intersect. Our own local group of galaxies is on a filament, moving toward the Virgo cluster, a massive concentration of galaxies about 53 million light-years away. And Virgo itself is part of a larger structure, the Laniakea supercluster we discussed earlier. Understanding the cosmic web helps us understand dark matter. Computer simulations of structure formation, using only gravity and dark matter, reproduce the filamentary structure remarkably well. This is strong evidence that dark matter exists and that it behaves the way we think it does. The cosmic web is dark matter's signature, the fingerprint of an invisible substance that outweighs normal matter 5 to 1. And the cosmic web is still evolving. Filaments are thinning as dark energy drives the accelerating expansion of the universe. Galaxy clusters are becoming more isolated. The voids are growing. In the far future, billions of years from now, the cosmic web will be less prominent. The universe will be more uniform, less structured, as expansion carries galaxies apart. Let's talk about something happening in our solar system that we only recently discovered: interstellar visitors, objects from other star systems passing through our solar system. We've detected 2 so far, Oumuamua in 2017 and Comet Borisov in 2019. But they're probably common. Astronomers estimate that at any given time, there might be hundreds or thousands of interstellar objects in the inner solar system. They're just too small and faint for us to detect. This has profound implications. It means the solar system is constantly being seeded with material from other star systems. Organic molecules, maybe even microorganisms in a dormant state, could be transported between star systems on these objects. This is called panspermia, the idea that life might spread through the galaxy, not through intentional travel, but passively, carried on comets and asteroids flung from one system and captured by another. Did life on Earth originate here, or did it arrive from somewhere else, carried on an interstellar visitor? We don't know. The chemistry required for life seems fairly straightforward. Carbon-based molecules can form in many environments, but the jump from chemistry to biology, from non-living molecules to self-replicating organisms, that's a mystery. Maybe it only happened once in the galaxy and spread via panspermia. Maybe it happens commonly wherever conditions are right. We need to find life elsewhere to answer that question. If we discover that life on Mars or Europa has a completely different biochemistry from Earth life, different DNA, different amino acids, that would suggest life arose independently at least twice in our solar system, which would imply it's common. But if life on Mars or Europa is biochemically similar to Earth life, that might suggest a common origin, possibly via panspermia. We're living in an era where we can finally start to answer these questions. We have rovers on Mars looking for signs of past or present life. We're planning missions to Europa and Enceladus to sample the water plumes jetting from their subsurface oceans. We're analyzing the atmospheres of exoplanets looking for biosignatures. In the next few decades, we might discover life elsewhere. Not intelligent life, probably. Not civilizations, but bacteria, microbes, single-celled organisms clinging to life in extreme environments. And that would change everything. That would tell us we're not alone. That the universe is alive with life, even if that life is simple. Let me tell you about an object that shouldn't exist but does. V391 Pegasi b. This is a gas giant planet orbiting a subdwarf B star, the exposed core of a star that was once a red giant. Here's the problem. When a star becomes a red giant, it expands enormously, engulfing anything in close orbit. V391 Pegasi b orbits at about 1.7 AU, roughly the distance of Mars from our Sun. When its star was a red giant, the star's outer layers would have extended past the planet's orbit. The planet should have been swallowed, vaporized, gone. But it's still there. Somehow it survived. Maybe it was further out originally and spiraled inward after the star lost its outer layers. Maybe it was just far enough away that tidal forces and friction didn't completely destroy it. Maybe we're missing something about how red giants and planets interact. Whatever the explanation, V391 Pegasi b is a survivor, a planet that endured its star's death throes and lived to tell the tale. And this gives us a preview of Earth's future. When the Sun becomes a red giant in about 5 billion years, it will expand beyond Earth's current orbit. Earth will probably be engulfed and destroyed, but maybe not. Maybe Earth will survive in a wider orbit, its surface scorched clean of any trace of oceans or atmosphere or life, but intact as a rocky cinder orbiting a white dwarf. Future alien astronomers, if they exist, might discover Earth billions of years from now, puzzle over its composition and orbit, and wonder what stories it could tell if only it could speak. Now let's talk about something truly mind-bending: closed time-like curves. These are solutions to Einstein's equations of general relativity where spacetime curves back on itself, creating paths through spacetime that loop, returning to their starting point not just in space but also in time. If you followed a closed time-like curve, you'd travel forward through time from your perspective, but eventually return to the moment you started, meeting your past self. Do closed time-like curves exist in reality? We don't know. The solutions that produce them involve exotic matter with negative energy density, or rotating black holes with unrealistic properties, or other conditions that might not be physically achievable. But the fact that Einstein's equations allow them, even in principle, suggests that time travel might not be forbidden by the laws of physics, just incredibly difficult or unlikely. And if time travel is possible, even in principle, it creates paradoxes. The grandfather paradox: if you travel back in time and prevent your grandparents from meeting, you would never be born, so you couldn't travel back in time to prevent them from meeting, so you would be born, so you could travel back in time, and so on. It's a logical loop with no resolution. Some physicists think paradoxes might be self-resolving. The universe might enforce consistency, preventing any action that would create a paradox. You could travel to the past, but you couldn't change anything significant. You'd be an observer, not a participant. Others think the many worlds interpretation of quantum mechanics resolves the paradoxes. When you travel to the past and change something, you create a branching timeline, a parallel universe where the change occurred while your original timeline remains unchanged. Or maybe closed time-like curves simply don't exist in nature. Maybe there's some principle we don't yet understand that prevents them from forming. The universe might have a built-in chronology protection, as Stephen Hawking called it, preventing time travel and preserving causality. We don't know, but the fact that we can even ask these questions, that general relativity allows for such bizarre possibilities, shows how strange the universe really is at a fundamental level. Let's discuss something more grounded: the habitable zone. This is the region around a star where conditions are right for liquid water to exist on a planet's surface, assuming the planet has an atmosphere. For our Sun, the habitable zone extends from about 95 cents, just inside Earth's orbit, to about $1.37, roughly midway between Earth and Mars. But the habitable zone isn't a fixed thing. It depends on the star's luminosity, which changes over time. When the Sun formed, it was about 70% as bright as it is now. Earth was near the inner edge of the habitable zone. As the Sun ages, it's getting brighter. Earth is moving toward the outer edge. Eventually, in about 1 billion years, Earth will be too hot, even without any additional greenhouse gases. The oceans will evaporate. The runaway greenhouse effect will begin. Earth will become uninhabitable. Mars, meanwhile, is currently outside the habitable zone, too cold for liquid water to exist on its surface. But as the Sun brightens, Mars will move into the habitable zone. In 1 billion years, Mars might be habitable while Earth is not. That's a strange thought. The red planet, cold and dead now, might be the warm, life-supporting world of the future, at least for a while. But we can manipulate the habitable zone in principle. Terraforming, the idea of deliberately modifying a planet to make it habitable, could move a planet into the effective habitable zone. We could warm Mars by releasing greenhouse gases into its atmosphere, thickening it, trapping heat. We could cool Venus by removing carbon dioxide from its atmosphere, though that's much harder. We could build mirrors in space to reflect sunlight away from a planet, cooling it, or focus sunlight onto a planet, warming it. This isn't science fiction. These are engineering problems, incredibly difficult, expensive, requiring centuries or millennia to complete, but not impossible. If humanity survives and spreads through the solar system, we might terraform Mars, Venus, even moons like Titan or Callisto. We might create habitable worlds where none existed before. And if we can do that, maybe other civilizations have done it too. Maybe some of the exoplanets we're discovering, worlds that seem just barely habitable, are actually terraformed, deliberately modified by the civilizations living there. We wouldn't be able to tell from our observations. A terraformed planet would look like a natural one, but the possibility exists. The universe might contain not just naturally habitable worlds, but artificially habitable ones too. I want to talk about extremophiles, organisms on Earth that live in conditions we once thought incompatible with life. Boiling hot springs with temperatures above the boiling point of water. Freezing Antarctic ice. Deep underground, kilometers below the surface. In rock with no sunlight and almost no water. Inside nuclear reactors, bathed in lethal doses of radiation. At the bottom of the ocean, around hydrothermal vents spewing toxic chemicals and superheated water. In the stratosphere, exposed to UV radiation and vacuum-like conditions. Even in space, on the outside of the International Space Station, some organisms can survive for years. Life is tougher than we thought, more adaptable, more resilient, and every extremophile we discover expands the range of environments we think could support life. If life can survive in boiling acid on Earth, it could survive in the sulfuric acid clouds of Venus. If life can survive in Antarctic ice, it could survive on Mars or Europa. If life can survive radiation, it could survive near magnetars or around black holes, at least for a while. This changes our expectations for where we might find life in the universe. We used to think life required very specific conditions. Liquid water, moderate temperatures, Earth-like atmosphere. Now we know life can adapt to almost anything. The habitable zone is much larger than we thought. Not just the region around a star where water is liquid, but anywhere there's liquid of any kind, any source of chemical energy, any way for metabolism to occur. Europa has a subsurface ocean. Enceladus has a subsurface ocean. Titan has methane lakes and a subsurface water ocean. Ganymede and Callisto might have oceans too. Even Pluto might have a subsurface ocean. Our solar system is full of potential habitats, places where life, if it can get started, might survive and even thrive. And if our solar system, which we once thought had only one habitable world, Earth, actually has a dozen or more potentially habitable environments, what does that imply for the galaxy? For the universe? There might be trillions of habitable worlds, trillions of places where life could exist. And if the origin of life is as straightforward as some scientists think, if life arises naturally wherever conditions allow, then the universe might be teeming with it. Not intelligent life necessarily, not civilizations, but life, microbes, simple organisms, survivors. We're not alone in the universe. We can't be. The odds are just too astronomical. Somewhere out there, on some moon or planet or rogue world drifting through the darkness, life exists. And maybe, just maybe, some of that life has evolved intelligence. Maybe somewhere, someone is looking up at their sky, wondering the same things we wonder, asking the same questions we ask. Let me bring this all together because everything I've told you, every strange phenomenon, every bizarre object, every impossible event, it all points to the same conclusion. The universe is under no obligation to make sense to us. We're biological creatures evolved on a single planet to survive in a very narrow range of conditions. We're good at understanding things on human scales, objects we can see and touch, times we can measure in seconds or years, speeds we can run or drive. But the universe operates on scales far beyond our everyday experience. It includes black holes and quantum foam, billion-year timescales and trillionth of a second events, objects moving at nearly the speed of light and distances that light takes billions of years to cross. And yet, somehow, we can understand it. Not perfectly, not completely, but we can build theories, test predictions, discover laws of nature that hold true across the entire observable universe. That's incredible. That's miraculous in a secular sense. The universe is comprehensible to minds that evolved to avoid predators and find food on an African savanna. Why? Why should the universe be understandable? Why should mathematics, an abstract system of logic invented by humans, describe physical reality so precisely? Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences, and it's a genuine mystery. We don't know why the universe follows mathematical laws. We don't know why we're capable of discovering those laws. We just are. Maybe it's anthropic. Maybe only in universes that follow comprehensible laws could intelligence evolve, because intelligence requires a predictable environment. If the universe were random, if laws of physics changed from moment to moment, intelligence couldn't develop. So the fact that we exist to ask the question implies we must live in a comprehensible universe. That's one possible answer. Or maybe there's something deeper. Maybe consciousness, intelligence, the ability to understand, is somehow built into the fabric of reality itself. Maybe the universe wants to be understood. Maybe it requires observers to give it meaning. That's more philosophical than scientific, but it's worth pondering. What I can tell you is this: we're living in a golden age of astronomy and physics. We're discovering things our ancestors couldn't have imagined. Gravitational waves, exoplanets, dark energy, the cosmic microwave background, quasars, pulsars, magnetars, black holes. We're seeing further, understanding more, asking deeper questions than ever before. And we're just getting started. In the next few decades, we'll launch telescopes that can see the atmospheres of Earth-like exoplanets. We'll detect more gravitational waves, mapping the population of black holes across the universe. We'll send probes to the moons of Jupiter and Saturn, searching for life. We might even detect technosignatures, signs of advanced civilizations, though that's a long shot. We might find that we're not just not alone in the universe, but that the universe is crowded with life and intelligence. Or we might find that we're alone, that life is so rare, intelligence so unlikely, that we're the only ones in the observable universe, maybe the only ones ever. That would be lonely, but also profound. It would mean we're special. Not in a cosmic sense, the universe doesn't care about us, but in the sense that consciousness, the ability to ask questions and seek answers, might exist only here, only now, in this brief moment of cosmic history. Either answer is astonishing. Either we're part of a vast community of living worlds, or we're a rare and precious anomaly. Either the universe is full of minds wondering about their place in the cosmos, or we're the only ones doing the wondering. Both possibilities are humbling and awe-inspiring in equal measure. But whatever the answer, we have a responsibility. If we're alone, we're the universe's only way of understanding itself, at least in this cosmic epoch, at least in this corner of space. If we're not alone, we're still unique, a particular expression of the universe's creativity, one path among many that led from chemistry to biology to intelligence. We have a responsibility to survive, to learn, to explore, to understand. We have a responsibility to preserve our planet, not just for ourselves, but for all the life that shares it with us. We have a responsibility to reach for the stars, to become a spacefaring species, to ensure that whatever happens to Earth, humanity or its descendants continue the project of understanding. The universe is vast and old and strange, full of phenomena that defy intuition and objects that challenge understanding. but it's also beautiful and knowable and filled with wonders. Every question we answer leads to new questions. Every mystery we solve reveals deeper mysteries. The universe is an infinite puzzle, and we've barely begun to assemble the pieces. But that's what makes it exciting. That's what makes it worth studying. Not because we'll ever understand everything, we won't, but because the act of trying to understand, the process of discovery, the joy of learning something new about how reality works, that's what makes us human. That's what gives meaning to our existence. So look up at the night sky. Think about the distances involved, the timescales, the energies, the strangeness of it all. Think about magnetars and hypervelocity stars and rogue planets and zombie stars. Think about the fact that you're made of atoms forged in the hearts of dying stars, that the iron in your blood was created in a supernova billions of years ago, that you're literally star stuff contemplating the stars. That's not a metaphor. That's literal truth. You are the universe experiencing itself. You are matter organized in such a way that it can think, wonder, ask questions. And that's extraordinary. That's beautiful. That's something worth celebrating. The cosmos is waiting. There are mysteries out there. Phenomena we haven't discovered yet. Questions we haven't thought to ask. And maybe, if we're very lucky and very careful and very persistent, we'll answer some of them. We'll push back the boundaries of ignorance just a little bit further. We'll understand the universe a little bit better. That's our purpose. That's our legacy. To explore, to discover, to understand. To look up at the infinite, impossible cosmos and say, we're trying to figure you out. We don't have all the answers. We might never have all the answers. But we're asking the questions. And that has to count for something. Let me tell you about pulsars, because these objects are so precise they put our best atomic clocks to shame. A pulsar is a rapidly rotating neutron star that emits beams of radio waves from its magnetic poles. As the star rotates, these beams sweep across space like a cosmic lighthouse. If one of those beams happens to point toward Earth, we detect a pulse. And these pulses are incredibly regular. Some pulsars rotate hundreds of times per second, and their timing is so stable we can predict when the next pulse will arrive to within microseconds, sometimes nanoseconds. The millisecond pulsar PSR J1748-2446 AD holds the record, rotating 716 times per second. That's a ball of neutrons, 20 kilometers across with 1.5 times the mass of the sun, spinning faster than a kitchen blender. At its equator, material is moving at about 24% the speed of light. If it spun any faster, it would tear itself apart, overcome its own gravity, and fly into pieces. We use pulsars as cosmic clocks. Astronomers have proposed using an array of pulsars to detect ultra-low-frequency gravitational waves, the kind produced by supermassive black hole binaries. The gravitational waves would stretch and compress space between Earth and the pulsars, causing tiny changes in the pulse's arrival times. We'd be using the galaxy itself as a gravitational wave detector, with pulsars as the measuring rods. That's happening right now. Projects like NANOGrav and the International Pulsar Timing Array are monitoring dozens of pulsars, looking for the correlated timing variations that would signal a gravitational wave passing through. And pulsars might be dangerous up close. The magnetic fields, the radiation, the relativistic particles streaming away from the poles, all of it would be lethal. If a pulsar's beam swept across Earth, even from hundreds of light years away, it might damage satellites, disrupt communications, possibly harm the ozone layer. We're lucky that most pulsars are not aimed at us, that their beams sweep through space in other directions, missing Earth entirely. Now let's venture to the early universe, to a time when things were very different from today. Quasars, quasi-stellar objects, are among the most luminous objects in the cosmos. They're supermassive black holes, billions of times the mass of the sun, actively feeding on enormous amounts of material. The accretion disks around these black holes shine so brightly they outshine entire galaxies. A single quasar can emit 1,000 times more light than the Milky Way, all from a region smaller than our solar system. Quasars were most common when the universe was young, a few billion years old. Back then, galaxies were still forming, merging, and there was plenty of gas available to feed supermassive black holes. Today, quasars are rare. Most supermassive black holes have run out of nearby fuel. They're quiescent, dormant like Sagittarius at the center of our galaxy. But in the early universe, quasars dominated. They regulated star formation in their host galaxies. They heated the intergalactic medium. They ionized hydrogen across vast regions of space. Quasars helped shape the universe into what we see today. Without them, galaxies would look different, the distribution of matter would be different, possibly even the formation of planets and life would be affected. When we look at distant quasars, we're seeing light that has traveled for billions of years. We're seeing the universe as it was when it was young, turbulent, still organizing itself. The most distant quasar we've found so far, J0313-1806, is seen as it was just 670 million years after the Big Bang. At that time, the universe was still in its infancy, and yet this quasar's black hole already had a mass of 1.6 billion solar masses. How did black holes grow so large so quickly? We don't fully understand. It's one of those mysteries that observations have revealed but theory hasn't yet explained. Let's talk about something genuinely terrifying: vacuum decay. According to quantum field theory, the vacuum of space, what we think of as empty space, exists in a particular energy state. But it might not be the lowest possible energy state. There might be a lower energy configuration, a true vacuum, and our current vacuum might be what's called a false vacuum, metastable, temporarily stable but not truly stable. If that's the case, then vacuum decay is possible. Somewhere, randomly, a tiny region of space could quantum tunnel into the true vacuum state. And once it starts, it doesn't stop. The true vacuum region expands at the speed of light, converting everything it touches. Inside the bubble of true vacuum, the laws of physics are different. Particle masses change. The strengths of fundamental forces change. Atoms as we know them cannot exist. If vacuum decay occurs, we wouldn't see it coming. The bubble would expand at the speed of light. There would be no warning. One moment, everything would be normal. The next moment, you'd be inside the bubble, and the atoms in your body would cease to exist in any meaningful way. You wouldn't have time to feel anything. You wouldn't even have time to start feeling something. You'd simply cease to be, along with Earth, the Sun, the galaxy, and eventually, if we wait long enough, the entire universe. Is this likely to happen? We don't think so. The universe has existed for almost 14 billion years without vacuum decay occurring, as far as we can tell. If it were likely, it probably would have happened already. But the fact that it's possible that the very fabric of spacetime might be unstable, that's unsettling. It's a reminder that the universe rests on quantum mechanical foundations, and quantum mechanics is fundamentally probabilistic. Unlikely things can happen, and given infinite time, unlikely things become inevitable. Let me tell you about the strangest orbits in the solar system, found in the distant Kuiper belt. Several trans-Neptunian objects have highly elongated orbits that are weirdly aligned with each other. Their orbits are tilted the same way. Their closest approaches to the Sun happen in roughly the same direction. This clustering is statistically unlikely to occur by chance. One explanation is that there's another planet out there, a ninth planet, several times the mass of Earth, orbiting far beyond Neptune in the distant reaches of the solar system. Its gravity would shepherd these smaller objects, aligning their orbits. Astronomers have been searching for this hypothetical Planet 9 for years, but so far, nothing. The sky is big. The planet, if it exists, is faint and far away. It might take decades to find, but maybe Planet 9 isn't a planet. Maybe it's a primordial black hole, a tiny black hole with just a few times Earth's mass, left over from the early universe. Such an object would be incredibly difficult to detect directly. It wouldn't emit light. It would be invisible, but its gravity would affect the orbits of Kuiper belt objects exactly the same way a planet would. Some scientists have proposed searching for Planet 9 by looking for its gravitational effects on passing comets or by looking for the glow of Hawking radiation, though that would be incredibly faint. Or maybe there's no Planet 9 at all. Maybe the orbital alignments are just a statistical fluke or the result of observational bias. We've only discovered a tiny fraction of trans-Neptunian objects. Maybe when we find more, the alignment will disappear, revealed as an artifact of incomplete data. The outer solar system is still largely unexplored. We've sent one spacecraft, New Horizons, through the Kuiper Belt, and it visited only 2 objects. There are probably hundreds of thousands of objects larger than 100 kilometers in the Kuiper Belt, and millions of smaller ones. What other surprises are lurking out there in the cold darkness beyond Neptune? Now let's talk about the ultimate fate of the universe, because it's not eternal. The universe had a beginning, the Big Bang, and it will have an end, though what that end looks like depends on dark energy. The current evidence suggests the universe will end in what's called heat death or the Big Freeze. The expansion of the universe will continue forever, accelerating due to dark energy. Galaxies will move apart. Star formation will slow as gas is used up. Eventually, all stars will burn out. White dwarfs will cool to black dwarfs. Neutron stars will sit alone in the darkness. Black holes will evaporate through Hawking radiation, taking googolls of years to do so. The universe will become a thin soup of particles, spread across infinite space, approaching absolute zero in temperature. Nothing will happen. Nothing can happen. The universe will be dead, dark, and silent forever. That's the most likely scenario, but there are alternatives. If dark energy strengthens over time, and there's some theoretical models where it does, we might face a big rip. In this scenario, the expansion accelerates so much that it eventually overcomes all forces, even the forces holding atoms together. First, galaxies are torn apart, then solar systems, then planets, then molecules, then atoms, then subatomic particles. The universe rips itself apart at every scale, ending in a catastrophic breakdown of space-time itself. This would happen in about 20 billion years if certain models of dark energy are correct. Or if dark energy reverses, if it becomes attractive instead of repulsive, we might face a big crunch. The expansion of the universe would slow, stop, and reverse. Everything would start falling back together. Galaxies would collide. The cosmic microwave background would heat up. Eventually, everything in the universe would merge into a single, infinitely hot, infinitely dense point, perhaps leading to another Big Bang, a cyclic universe that expands and contracts forever. We don't know which fate awaits the universe. We're measuring the properties of dark energy as precisely as we can, trying to determine if it's constant, strengthening, or weakening. But all 3 scenarios lead to the end of everything we know. The universe is finite in time, even if it's infinite in space. Everything that exists now will eventually end. Does that depress you? It shouldn't. We have trillions of years. The stars will shine for trillions of years. Life could persist for trillions of years, adapting to the changing universe, perhaps learning to harvest energy from black holes, surviving long after stars have gone dark. And who knows what intelligence might accomplish given that much time. Perhaps it will find a way to escape the dying universe, to create new universes, to transcend the limitations of space-time itself. Or perhaps it will simply watch the universe wind down, bearing witness to the end of all things. Either way, we're here now, in the universe's prime, when stars shine and galaxies spiral and planets orbit and life flourishes. We're living in a special time, cosmically speaking, and that's worth appreciating. Let me tell you about planetary migration, because planets don't always stay where they form. In the early solar system, the giant planets weren't where they are now. Jupiter might have formed further out and migrated inward, then been pulled back outward by Saturn. Neptune might have formed closer than Uranus and been scattered outward. These migrations would have disrupted the orbits of smaller bodies, flinging them throughout the solar system. The Late Heavy Bombardment, a period about 3.9 billion years ago when the inner solar system was pelted with asteroids and comets, might have been caused by planetary migration. Neptune, moving outward, disturbed the Kuiper belt, sending icy bodies careening inward. Some hit Earth. Some hit the Moon, creating the large craters we still see today. And ironically, those impacts might have delivered water and organic molecules to Earth, seeding our planet with the ingredients for life. We see planetary migration in exoplanet systems too. Hot Jupiters, gas giants orbiting incredibly close to their stars, closer than Mercury orbits our sun, couldn't have formed there. It's too hot. They must have formed further out and migrated inward, perhaps through interactions with the protoplanetary disk or with other planets. Some of these migrations might have ejected smaller, rocky planets from the system entirely, flinging them into interstellar space as rogues. Planetary systems are dynamic, evolving over millions and billions of years. The nice, orderly arrangement of planets we see in our solar system today is not how things started. It's the result of 4.5 billion years of gravitational interactions, collisions, near misses, and migrations. We're seeing a snapshot, a single moment in a process that's still ongoing, just much more slowly now than in the early days. Now I want to talk about something that challenges our deepest assumptions about reality: the measurement problem in quantum mechanics. When we measure a quantum system, it collapses from a superposition of states into a single definite state. Before measurement, a particle can be in multiple places at once, spinning both up and down, existing in a probabilistic cloud of possibilities. After measurement, it's in one place, one spin, one definite state. But what counts as a measurement? Does it require a conscious observer, or is any interaction enough? If a particle interacts with a piece of dust in space, far from any observer, does it collapse? Or does the particle, the dust, and eventually the entire universe remain in superposition until someone looks? This is the measurement problem, and despite a century of quantum mechanics, we still don't have a universally accepted answer. Some interpretations, like the Copenhagen interpretation, say that measurement causes collapse, but don't explain what measurement really means. Others, like the many worlds interpretation, say there's no collapse at all. Every quantum possibility is realized, but in different branches of reality. When you measure a particle spin, the universe splits into two branches, one where you measured spin up, another where you measured spin down. Both outcomes occur, but in separate, non-interacting universes. If many worlds is correct, and I want to emphasize that this is one interpretation among several, then every quantum event creates branching timelines. The number of parallel universes increases exponentially with each passing moment. There are versions of you reading these words where the next word is different, where I chose a different example, where history unfolded differently because a single particle zigged instead of zagged billions of years ago. Is this real? We don't know. We can't test it directly because we can't access other branches. But the mathematics of quantum mechanics seems to describe a multiverse whether we like it or not. Maybe that's just a mathematical artifact. Maybe it's telling us something profound about the nature of reality. We're still figuring it out. Let me tell you about something beautiful: the cosmic distance ladder. This is how we measure distances in the universe, and it's a remarkable achievement of human ingenuity. For nearby objects, we use parallax, measuring how a star's position shifts as Earth orbits the Sun. For more distant objects, we use standard candles, objects with known intrinsic brightness. If we know how bright something actually is and we measure how bright it appears, we can calculate its distance. Cepheid variable stars are excellent standard candles. They pulsate with a period that's related to their luminosity. Measure the period, and you know the intrinsic brightness. Type Ia supernovae are even brighter, visible across vast cosmic distances. By carefully calibrating these standard candles using nearby objects measured with parallax, we've built a distance ladder reaching billions of light years into space. And that's how we discovered dark energy. By measuring the distances to supernovae in distant galaxies and comparing them to the redshifts of those galaxies, astronomers discovered that the expansion of the universe is accelerating. Distant supernovae are dimmer than they should be, meaning they're farther away than expected for their redshift. Something is pushing space apart, and that something is dark energy. This discovery, made in 1998, won the Nobel Prize and revolutionized cosmology. We now know that dark energy makes up about 68% of the universe's total energy content. Dark matter makes up about 27%. Normal matter, everything we can see and touch, everything we're made of, is only about 5%. We're a rounding error in the cosmic inventory, and we still don't know what dark energy is. The leading theory is that it's the energy of empty space itself, the cosmological constant that Einstein introduced and then rejected. But when we calculate what that energy should be, we get an answer that's 10 to the power of 120 times larger than what we observe. That's not just wrong. That's spectacularly, embarrassingly wrong. It's the worst prediction in the history of physics. Something is wrong with our understanding. Either our calculation is flawed, or dark energy is something else entirely. Some new field or force we haven't discovered yet. Solving the dark energy problem might require new physics, a deeper theory that goes beyond general relativity and quantum field theory. Or it might require rethinking our most basic assumptions about space, time, and energy. Let me tell you about aurora, but not on Earth. On Jupiter, Saturn, Uranus, Neptune, aurora are caused by the same basic mechanism as on Earth. Charged particles funneled by magnetic fields to the poles, where they collide with atmospheric gases and produce glowing curtains of light. But the details are fascinating. Jupiter's aurora are powered primarily by its volcanic moon Io, which spews sulfur and oxygen into space. These particles get ionized and trapped in Jupiter's powerful magnetic field, creating a torus of plasma around the planet. As Jupiter rotates, this plasma is flung outward and then crashes back down onto the poles, creating aurora hundreds of times more energetic than anything on Earth. Jupiter's aurora shine in ultraviolet, X-rays, even infrared. They're permanent features, always present, glowing at all times. Saturn's aurora are similar but also interact with its rings. Charged particles from the solar wind get channeled along magnetic field lines connected to the rings, creating localized auroral displays. Saturn's aurora pulse and flicker in response to changes in the solar wind. And here's something weird. We've detected aurora on exoplanets. Some hot Jupiters, gas giants orbiting very close to their stars, show radio emissions consistent with enormous auroral activity. These planets are being blasted by stellar wind much more intense than anything in our solar system. Their aurora might be bright enough to see invisible light, glowing planets lit by their own magnetic interactions. If you could stand on a hot Jupiter, and you absolutely could not survive the heat and radiation, the sky would be ablaze with aurora, sheets of light dancing overhead, energized by the relentless stream of particles from the nearby star. It would be beautiful and deadly, a light show powered by forces that would tear apart any biological matter. Let me tell you about the sound of the universe, because space isn't completely silent. The cosmic microwave background has variations, hot and cold spots, that represent sound waves in the early universe. Before atoms formed, about 380,000 years after the Big Bang, the universe was a plasma of electrons and protons. Photons couldn't travel far without being scattered. But sound waves could propagate through this plasma, compressions and rarefactions traveling at about 57% the speed of light. These sound waves were created by quantum fluctuations in the inflating early universe. They propagated outward, creating regions of higher and lower density. When atoms finally formed and the universe became transparent, those density variations were frozen in place, visible today as temperature variations in the cosmic microwave background. We can analyze these variations, measure their scale, their amplitude, their distribution. And from that analysis, we can determine the composition of the universe, the amount of normal matter, dark matter, and dark energy. We can measure the geometry of space, determining that it's flat or very close to flat. We can test theories of inflation, constraining what happened in the first fraction of a second after the Big Bang. In a sense, we're listening to the oldest sound in the universe, the echo of creation itself, transformed from sound waves into light patterns and now into data we can analyze. The universe is telling us its story, and we've learned to listen. Now, let me bring this journey to a close because we've traveled far together, from the strange dimming of distant stars to the quantum foam of spacetime, from magnetars to multiverses, from the coldest laboratories on Earth to the hottest quasars in the early universe. We've explored phenomena that defy intuition, objects that challenge our understanding, and events that remind us how little we truly know. But here's what strikes me most about all of this. Every single phenomenon I've described, every strange object, every impossible event, exists because the universe follows rules. Not arbitrary rules. Not rules that change on a whim, but consistent, mathematical, testable rules. The laws of physics work the same way everywhere, from the surface of Earth to the edge of the observable universe, from the Big Bang to the far future. That's extraordinary. The universe could have been chaos, could have been random, could have been incomprehensible, but it's not. It's structured, it's ordered, it follows patterns we can discover and understand. A neutron star obeys the same laws of gravity that govern a falling apple. A quasar billions of light years away operates by the same principles of physics that power our sun. Quantum mechanics works the same way in a laboratory in Japan as it does in the heart of a distant galaxy. This universality, this consistency, is what makes science possible. It's what allows us to learn about the cosmos from our tiny planet. We don't have to visit a black hole to understand it. We can do the mathematics, run simulations, test predictions, and be confident that our conclusions apply to real black holes across the universe. That's power. That's remarkable. And yet, the universe continues to surprise us. Every time we build a better telescope, a more sensitive detector, a more powerful computer, we discover something new, something we didn't predict, something that forces us to revise our theories, expand our understanding, acknowledge our ignorance. The universe is consistent, but it's not simple. It's layered, complex, full of emergent phenomena that arise from simple rules but produce outcomes we couldn't have foreseen. We're living in a universe that's simultaneously comprehensible and mysterious, ordered and strange, beautiful and terrifying. It contains wonders that inspire awe and dangers that could annihilate us without warning. It's vast beyond imagining, yet governed by laws we can write in equations. It's ancient beyond comprehension, yet still evolving, still changing, still creating new structures and destroying old ones. And we're part of it. Not separate observers looking at the universe from outside, but participants made of the same matter, following the same laws, subject to the same forces. When we study the universe, we're studying ourselves. When we ask where the universe came from, we're asking where we came from. When we wonder about the universe's fate, we're contemplating our own ultimate destiny. This connection, this fundamental unity between us and the cosmos, is what makes astronomy and physics not just sciences but philosophies, not just intellectual pursuits but spiritual journeys. Understanding the universe changes how we see ourselves. It reveals our place in the cosmic story, our role in the unfolding of natural law. We're not the center of the universe. We're not the purpose of creation. We're not special in any cosmic sense. Earth is a pale blue dot, as Carl Sagan said, a mote of dust suspended in a sunbeam. Humanity has existed for a cosmological eye blink. We'll be gone in another eye blink, at least in our current form. The universe doesn't need us. It was fine for nearly 14 billion years before we showed up, and it'll be fine for trillions more after we're gone. But that doesn't make us insignificant. It makes us remarkable. Against all odds, against entropy and chaos and the vast cold indifference of space, matter organized itself into life, and life organized itself into consciousness, and consciousness organized itself into intelligence capable of asking why. We're the universe's way of knowing itself. We're the means by which the cosmos examines its own existence. We're matter that wonders about matter, energy that contemplates energy, patterns seeking to understand the rules that create patterns. That's not nothing. That's everything. So when you look up at the night sky, when you think about magnetars and quasars and black holes and dark energy, remember that you're not just learning facts. You're participating in one of humanity's greatest achievements, the systematic attempt to understand reality. You're part of a tradition stretching back thousands of years, to the first humans who looked up and wondered, to the philosophers who proposed that nature follows rational laws, to the scientists who tested those laws and found them true. Every question you ask contributes to that tradition. Every moment you spend contemplating the cosmos adds to our collective understanding. You don't need a PhD. You don't need a telescope. You just need curiosity and a willingness to think, to wonder, to let your mind range across the vast scales of space and time. The universe is strange. The universe is beautiful. The universe is vast and ancient and filled with phenomena that challenge everything we think we know. But the universe is also knowable, and that's the greatest wonder of all. We stand on Earth, a small planet orbiting an average star in an ordinary galaxy, looking outward at a cosmos 13.8 billion years old and 93 billion light-years across, and we understand it. Not completely, not perfectly, but we understand it. We know where stars come from. We know how galaxies form. We know what happened in the first seconds after the Big Bang. We know what will happen trillions of years in the future. We've decoded creation and glimpsed the end of everything. That's what consciousness does. That's what intelligence achieves. That's what makes us, despite our insignificance on cosmic scales, absolutely vital on human scales. We're the universe waking up, looking around, and figuring out where it is. So keep looking up, keep asking questions, keep seeking answers. The cosmos has been waiting 14 billion years for someone to understand it. That someone is you. That someone is all of us. And together, we're doing something extraordinary. We're unusual phenomena too, after all. Conscious matter in a vast, unconscious universe. Organisms that can contemplate infinity. Creatures that can trace their lineage back to the Big Bang itself and forward to the heat death of everything. We're made of atoms forged in stellar cores, organized by evolution, powered by ancient sunlight, gazing outward at the very mechanisms that created us. If that's not unusual, if that's not a phenomenon worth celebrating, then nothing is. The universe is strange, and so are we, and that's exactly as it should be. It explains why the moon is so large relative to Earth. It explains the angular momentum of the Earth-Moon system. But there are problems. For one, the moon's composition is too similar to Earth's. If Theia was a separate body, it should have a different isotopic signature, different ratios of elements. But the moon and Earth are nearly identical in their oxygen isotopes, their titanium isotopes. It's as if the moon is made entirely from Earth's mantle, with no contribution from Theia. But if that's the case, where did Theia go? Some propose that Theia was isotopically identical to Earth by coincidence, that it formed in the same region of the solar nebula. But that seems unlikely. Others propose that the impact mixed the material so thoroughly that Theia's signature was erased. But simulations struggle to reproduce that level of mixing. Another problem is the moon's orbit. Initially, it should have been in Earth's equatorial plane, but it's tilted. Something perturbed it, and we're not sure what. These might seem like minor issues, but they're not. The giant impact hypothesis is the leading theory, but it's not perfect. And until we understand the discrepancies, we can't be confident that we've got it right. The moon is right there, 250,000 miles away, and we've sent people to walk on it. But we still don't fully understand how it came to be. That's humbling. Let's discuss dark flow. In the early 2000s, astronomers noticed something strange. Galaxy clusters are moving in a particular direction toward a region of the sky at hundreds of kilometers per second. This motion is on top of the Hubble expansion. It's as if something outside the observable universe is pulling galaxy clusters toward it. This was called dark flow, and it was controversial from the start. Other teams tried to replicate the result and failed. The signal disappeared in more recent data. It might have been a statistical fluke, an artifact of how the data was processed. But for a while, it was tantalizing. If dark flow were real, it would imply structure beyond the cosmic horizon, regions of the universe we can never see, exerting gravitational influence on our local neighborhood. It would mean the observable universe is a small patch in something much larger, and the larger structure has its own dynamics, its own flow. Even if dark flow isn't real, the question remains: is there something beyond the horizon? In principle, the universe could extend infinitely, or it could be finite and closed. We can't see beyond the horizon, so we can't know. We're trapped in a bubble, and we can only infer what lies outside by its effects on what we can see. It's like being in a room with no windows. You can hear sounds from outside, feel vibrations through the walls, sense hints of a larger world, but you can't see it directly. That's our situation in cosmology. We're in a room and we're trying to deduce the shape of the building, the layout of the city, the size of the planet, all from indirect clues. Here's another one: the Eridanus supervoid. It's a region of space about 1 billion light-years across where there are far fewer galaxies than average. Voids are common in the large-scale structure of the universe, but this one is unusually large, and it corresponds to a cold spot in the cosmic microwave background, a region where the temperature is slightly lower than average. The cold spot was detected by the WMAP satellite and confirmed by Planck. It's statistically anomalous, unlikely to occur by chance. Some have proposed that it's caused by the supervoid, that photons lose energy climbing out of the gravitational well of the void, creating a cold spot. But the effect is too small. The void can't fully explain the cold spot. So what's going on? Is it a statistical fluke, a rare fluctuation that we happened to find because we looked hard enough? Is it a sign of new physics, a window, or even a bruise from a collision with another universe in the multiverse? We don't know. The cold spot sits there, in the southern sky, colder and larger than it should be, a blemish on the cosmic microwave background, unexplained and unsettling. Now let me talk about something truly strange: the delayed choice quantum eraser experiment. It's one of the most mind-bending experiments in quantum mechanics, and it shows that the future can affect the past, in a sense. Here's how it works. You send photons through a double slit, creating an interference pattern. Then you tag the photons, marking which slit they went through. The interference pattern disappears because you've measured the path. But then, after the photons have already passed through the slits, you erase the witch path information. The interference pattern reappears. So far, so quantum. But here's the twist. You can delay the erasure, perform it after the photon has hit the detector. And even then, the interference pattern reappears, retroactively. The photon knows that its witch path information will be erased in the future, and it behaves accordingly in the past. This doesn't allow you to send information backward in time, for subtle reasons involving how you sort the data. But it shows that causality in quantum mechanics is slippery. The future influences the past, or rather, the distinction between past and future breaks down at the quantum level. What does this mean? It means that time is not as fundamental as we think. Events don't have a fixed order. They're tangled, interwoven, retroactively determined by future measurements. Reality is negotiated between past and future, and the present is just where the negotiation happens. This has implications for the nature of time, for free will, for everything. If the future affects the past, then the past isn't fixed. It's probabilistic, contingent on what happens later. History is fluid, constantly rewritten by the future. And that's deeply weird. Let's talk about neutrinos. They're ghostly particles, barely interacting with matter. Trillions pass through your body every second, and you never notice. They're produced in the sun, in supernovae, in nuclear reactors, in the atmosphere. They're everywhere, but they're almost impossible to detect. We've built massive detectors, buried deep underground to shield them from cosmic rays. We fill them with thousands of tons of water or ice, and we wait for a neutrino to interact, producing a flash of light. It happens maybe once a day. Neutrinos are elusive, but here's the thing. Neutrinos have mass. We thought they were massless for decades, but experiments showed they oscillate between different flavors, and that's only possible if they have mass. This was a major discovery, Nobel Prize winning, because it means the standard model of particle physics is incomplete. The standard model assumes massless neutrinos. Reality disagrees, but we don't know how much mass they have. We know it's tiny, less than a millionth the mass of an electron, but we don't know the exact value. And we don't know if there are other types of neutrinos, sterile neutrinos, that don't interact even through the weak force. Some experiments have hinted at sterile neutrinos. Other experiments have ruled them out. The data is contradictory, frustrating. And sterile neutrinos, if they exist, could be dark matter. They could be the missing mass in the universe, hiding in plain sight, or rather, hiding because they're invisible. Neutrinos also violate a symmetry called CP symmetry, which combines charge conjugation and parity. This violation is necessary to explain why the universe has more matter than antimatter. Without it, matter and antimatter would have annihilated in the early universe, leaving only photons. We wouldn't exist. But the amount of CP violation in neutrinos isn't enough to explain the matter-antimatter asymmetry. There must be other sources, other processes that we haven't discovered. Neutrinos are a clue, but they're not the whole answer. And then there's the solar neutrino problem, which was a mystery for decades. The sun produces neutrinos through nuclear fusion, and we can calculate how many should reach Earth. But when we detected them, we found only about a third of the expected number. Were our models of the sun wrong? Were the detectors malfunctioning? The answer turned out to be neutrino oscillation. Electron neutrinos produced in the sun convert to muon and tau neutrinos on the way to Earth, and the early detectors could only see electron neutrinos. Once we built detectors sensitive to all flavors, the numbers matched. The sun was fine. Neutrinos were just more interesting than we thought. This is a victory for science, a mystery solved. But it's also a reminder that even our sun, the star we study most closely, can surprise us. Let me tell you about the Great Attractor. It's a gravitational anomaly, a region of space toward which our galaxy and millions of others are being pulled. It's hidden behind the zone of avoidance, a region of the sky obscured by the dust and gas of our own galaxy. We can't see it directly. We can only infer its existence from the motion of galaxies. The Great Attractor is enormous, with the mass of tens of thousands of galaxies. It's pulling us toward it at 600 kilometers per second. But it's not the end of the story. Beyond the Great Attractor is an even larger structure, the Shapley supercluster, a concentration of mass so vast that it influences the motion of galaxy superclusters across hundreds of millions of light-years. We're caught in a cosmic flow, drifting toward concentrations of mass we can barely see. It's humbling, We like to think of space as empty, but it's full of structure, full of gravity wells and filaments and voids. We're floating in a web and we're not in control. The large-scale structure of the universe looks like a sponge or a neural network. Galaxies cluster into filaments, separated by voids. The filaments intersect at nodes, galaxy superclusters, the largest gravitationally bound structures in the universe. And the whole thing is expanding, driven by dark energy, stretching the web tighter. If you could see the universe from outside, you'd see this pattern, this cosmic web, and it's beautiful. It's the result of gravity amplifying tiny quantum fluctuations in the early universe, turning them into the galaxies and clusters we see today. Structure emerged from chaos, order from randomness, through the simple action of gravity over billions of years. But there's a puzzle. The universe is too structured. Simulations of structure formation, based on dark matter and dark energy, predict a certain amount of clustering. But observations show more clustering than expected. The universe has lumpier than it should be. This is called the sigma-8 tension, and it's one of several tensions in cosmology right now. Different measurements of the same quantities give different answers. The Hubble constant, the rate of expansion, differs depending on how you measure it. The amount of matter in the universe differs. The amplitude of fluctuations differs. These might be measurement errors. They might be systematic effects we haven't accounted for. Or they might be signs of new physics, cracks in the standard model of cosmology. We won't know until we get more data, better data, and that takes time and money and effort. But the tensions are exciting because they suggest we're on the verge of something. A new discovery, a new understanding, a paradigm shift, or maybe just a better model. Either way, cosmology is entering a new phase where precision measurements are revealing discrepancies, and discrepancies are where breakthroughs hide. Now let's talk about vacuum decay again, because it deserves more attention. The idea is that the vacuum we live in, the lowest energy state of empty space, might not be the true vacuum. It might be a false vacuum, a metastable state that could decay to a lower energy state. If this happens, a bubble of true vacuum nucleates somewhere, expanding at the speed of light. Inside the bubble, the Higgs field has a different value. Particles have different masses. The electromagnetic force has a different strength. Chemistry doesn't work the same way. Atoms can't form. Everything is destroyed and replaced by a new kind of matter, governed by new laws. This is called vacuum decay or vacuum metastability, and it's not just theoretical. The shape of the Higgs potential, measured at the Large Hadron Collider, suggests that we might be in a metastable state. The vacuum might be on the edge of stability. The good news is, even if we're metastable, the decay rate is incredibly low. The probability of a bubble nucleating in any given region of space, in any given second, is vanishingly small. We're safe for trillions upon trillions of years, far longer than the current age of the universe. But here's the catch. Quantum tunneling isn't the only way to trigger vacuum decay. High-energy processes like those in the early universe or near black holes could push the Higgs field over the barrier. And if vacuum decay has happened elsewhere in the universe, the bubble walls are expanding at light speed. One could reach us at any moment. There's no way to detect it, no way to prepare, no way to survive. The bubble wall would hit us, and we'd cease to exist, replaced by a new vacuum with new physics. It's the ultimate existential threat, unavoidable, unpredictable, and absolute. Does this keep me up at night? Not really. The probability is so low that worrying about it is irrational. But it's a reminder that the universe is not a safe place. It's a place where laws can change, where stability is temporary, where everything we know could be erased in an instant by processes we barely understand. And yet, here we are. The vacuum hasn't decayed yet. We're still here, contemplating these possibilities, marveling at the universe's complexity and danger. That counts for something. Let me end with the biggest mystery of all: consciousness. What is it? How does it arise? Why does anything have subjective experience? This is called the hard problem of consciousness, and it's genuinely hard. We have no idea how to bridge the gap between physical processes and subjective experience. You can explain how neurons fire, how signals propagate, how the brain processes information. You can map the neural correlates of consciousness, the brain regions that light up when you're aware. But none of that explains why there's something it's like to be you, why the lights are on, why you experience redness when you see red, instead of just processing wavelengths of light. Some argue that consciousness is an illusion, that there's no hard problem because there's nothing to explain. But that doesn't work. The one thing you can't doubt is your own experience. Even if everything else is an illusion, the illusion itself is real. There's something it's like to be fooled. Others argue that consciousness is fundamental, that it's a basic feature of the universe like space or time or mass. This is panpsychism, and it's gaining traction among philosophers and some physicists. If consciousness is fundamental, then the hard problem dissolves. You don't have to explain how it emerges because it doesn't emerge. It's always there, woven into the fabric of reality. But that raises new questions. If consciousness is fundamental, then everything is conscious, at least to some degree. Electrons are conscious. Photons are conscious. Rocks are conscious. This seems absurd, but maybe our intuitions are wrong. Maybe consciousness comes in degrees, and human consciousness is just a particularly complex form. Integrated information theory tries to quantify this. It says consciousness is a measure of how integrated and differentiated a system is. A brain has high integrated information because its parts work together in complex ways. A collection of isolated neurons has low integrated information. A rock has even less. But this leads to strange conclusions. According to integrated information theory, certain networks, even non-biological ones, could be conscious if they have enough integrated information. A grid of logic gates arranged the right way could be conscious. A sufficiently complex computer program could be conscious. And maybe certain physical systems, like some crystal lattices, have low but non-zero consciousness. This sounds like science fiction, but it's serious science. And if it's true, it means consciousness is everywhere in varying degrees, and we're just one point on a spectrum that extends from rocks to gods. Alternatively, consciousness might be quantum. Some argue that the brain exploits quantum effects, that microtubules in neurons are quantum computers, and consciousness arises from quantum coherence and entanglement. This is called orchestrated objective reduction, proposed by Roger Penrose and Stuart Hameroff. The problem is, the brain is warm and wet, not the kind of environment where quantum effects usually survive. Decoherence happens almost instantly. How could the brain maintain quantum coherence long enough to do anything useful? We don't know. Maybe biology has found a way. Maybe quantum effects are protected in certain structures. Maybe consciousness requires quantum mechanics. Or maybe not. Maybe consciousness is purely classical, emerging from the complexity of neural networks. Maybe it's a matter of organization, not substrate. Maybe any system with the right kind of feedback loops and information processing will become conscious, regardless of whether it's made of neurons or silicon. We don't know, and that's the point. Consciousness is the last great frontier. We've split the atom, mapped the genome, photographed black holes. But we still don't understand what it's like to be anything. And here's the final twist. If we don't understand consciousness, then we don't fully understand ourselves. We're mysteries to ourselves, and that's both humbling and exhilarating. It means there's still so much to discover, not just out there in the cosmos, but in here, in the 3 pounds of tissue between your ears. You are the universe becoming aware of itself. You are stardust contemplating stars. And you are fundamentally inexplicable, at least for now. So here's where we are. We live in a universe we don't understand. We're made of particles whose properties we can barely explain. We're conscious and we don't know why. We're alone or we're not, and we don't know which is true. We're searching for answers, and every answer leads to more questions. But that's okay. That's the process. That's science. It's not about certainty. It's about curiosity. It's about looking at the darkness and saying, I wonder what's out there, and then building a telescope to find out. The paradoxes that keep scientists awake at night are the same paradoxes that should keep all of us awake. Not with fear, but with wonder, because these aren't just abstract problems. They're questions about the nature of reality, about who we are, about where we came from and where we're going. And we're privileged to live in a time when we can ask these questions and have a reasonable hope of answering some of them. Not all, maybe not even most, but some. And that's enough. The universe is vast and strange and beautiful and terrifying. It doesn't care about us. It doesn't owe us anything. But it gave us minds capable of understanding it, at least in part. And that's a gift beyond measure. So keep asking, keep wondering, keep probing the boundaries of the known. Because out there, in the darkness, in the silence, in the quantum foam and the cosmic web and the singularities and the horizons, there are answers. And maybe, just maybe, we'll find them. Or maybe we won't. Maybe some questions are unanswerable. Maybe the universe is under no obligation to make sense to us. Maybe we're limited, finite, doomed to see only shadows on the wall of Plato's cave, forever cut off from the full truth. But even so, we'll keep trying, because that's what we do. That's what it means to be human. We reach for the stars, even knowing we might never grasp them. We ask why, even when there's no answer. We build, explore, discover, create meaning in a cosmos that started without it. And that's not futile. That's beautiful. These cosmic paradoxes, these impossible questions, they're not obstacles. They're invitations. The universe is saying, come, explore, wonder. There's more here than you ever imagined. And we're responding. With telescopes and particle accelerators and mathematical theorems and late nights staring at equations that don't quite work. We're pushing back the darkness, one photon at a time, one calculation at a time, one insight at a time. Will we solve all the paradoxes? Probably not, but we'll solve some. And in solving them, we'll uncover new ones, deeper and stranger than before. The frontier of knowledge never stops expanding. There's always another layer, another mystery, another question, and that's perfect, because a universe without mysteries would be a universe without discovery. And a universe without discovery would be a universe without wonder. And a universe without wonder would be unbearable. So embrace the paradoxes. Let them confound you, challenge you, inspire you. Let them remind you that reality is richer than any story we tell about it. Let them keep you humble, keep you curious, keep you searching. Because the universe is waiting. It has secrets to share. If we're brave enough to look, smart enough to listen, patient enough to learn. The night sky is full of questions, and somewhere in the darkness between the stars are the answers. We just have to find them. Let me tell you about the faint young sun paradox. For billion years ago, the sun was only about 70% as bright as it is today. Stars get brighter as they age, fusing hydrogen into helium, increasing their core density and temperature. So the early Earth should have been frozen solid, a snowball world where life could never have started. But it wasn't. We have geological evidence of liquid water on Earth's surface going back almost 4 billion years. We have fossils of microbial life from 3.5 billion years ago. The Earth was warm enough for life, even though the sun was dim. How? The answer might be greenhouse gases. Early Earth had a thicker atmosphere, rich in carbon dioxide and methane, trapping heat and keeping the planet warm. But the numbers don't quite work. You need implausibly high concentrations of greenhouse gases to compensate for the dim sun. And there's evidence that carbon dioxide levels weren't that high. Maybe clouds played a role. Fewer clouds mean less reflection of sunlight, more warming. Maybe the Earth's rotation was faster, creating different atmospheric circulation patterns. Maybe there were periods of freezing, and life survived in refugia, pockets of warmth near volcanic vents or impact craters. Or maybe our understanding of stellar evolution is wrong. Maybe the sun was brighter in the past than we think, or maybe it varied more than we expect. But that seems unlikely. We understand stellar physics pretty well, and the sun is a standard main sequence star. The faint young sun paradox remains unsolved. It's a reminder that even Earth's history, our own planet's story, contains mysteries. We don't fully understand how we got here, how life survived, how the conditions for our existence were maintained for billions of years. Now let's talk about gamma ray bursts, the most energetic explosions in the universe since the Big Bang. They release more energy in a few seconds than the sun will emit in its entire 10 billion year lifetime. They're so bright that we can see them from across the observable universe. There are two types. Short gamma ray bursts last less than 2 seconds and are caused by colliding neutron stars or a neutron star merging with a black hole. Long gamma ray bursts last more than 2 seconds and are caused by collapsing massive stars, hypernovae that form black holes. When a gamma ray burst goes off, it releases a collimated jet of radiation, a beam of gamma rays traveling at nearly the speed of light. If that beam is pointed at Earth, we see a gamma ray burst. If it's pointed elsewhere, we miss it, which means for every burst we see, there are hundreds we don't. The energy involved is staggering. A typical long gamma ray burst releases about 10 to 44 joules in a few seconds. That's 100 times more energy than the sun will emit in its entire lifetime, compressed into seconds. If a gamma ray burst went off in our galaxy, pointed at Earth, it would be catastrophic. The gamma rays would strip away the ozone layer, exposing the surface to lethal ultraviolet radiation. Mass extinction would follow. In fact, some paleontologists think a gamma ray burst might have caused the Ordovician extinction about 450 million years ago, when 60% of marine species died. There's no direct evidence, but the timing is suggestive, and gamma ray bursts are common enough that Earth should be hit by one every few hundred million years. But here's what puzzles me. Gamma ray bursts are so powerful, so concentrated, that they seem to violate energy conservation. Where does all that energy come from? The collapsing star has gravitational potential energy, rotational energy, magnetic energy. But when you add it all up, it's not enough. You need an efficiency close to 100%, converting mass directly into gamma rays. That's hard to do. The leading model involves black hole accretion. The collapsing core forms a black hole surrounded by a disk of infalling matter. The disk is incredibly hot, incredibly dense, and magnetic fields channel energy into jets that punch through the star and blast into space. This can explain the energy, but the details are murky. We can't simulate it accurately because the physics is too complex, involving general relativity, magnetohydrodynamics, nuclear reactions all at once. And then there's the mystery of ultra-long gamma-ray bursts, which last tens of minutes to hours. What could sustain such a long burst? A massive star collapsing doesn't take that long. Maybe it's a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, spinning down and releasing energy. Maybe it's a tidal disruption event, a star being torn apart by a supermassive black hole. We're not sure. Every gamma-ray burst is different. Some have afterglows that last for weeks, fading slowly as the jet interacts with surrounding material. Others fade in hours. Some produce gravitational waves, detected by LIGO when neutron stars collide. Others don't. The diversity suggests multiple mechanisms, multiple pathways to the same explosive endpoint. And we're seeing them from the early universe, from when the cosmos was young and stars were just forming. Gamma-ray bursts are beacons, illuminating the distant past, showing us what the universe looked like billions of years ago. They're also laboratories, places where physics operates under extreme conditions we can never reproduce on Earth. Let me take you to the edge of a black hole. Not the event horizon, but closer. The ergosphere. It's a region outside the horizon where space-time itself is dragged along by the black hole's rotation. If you were in the ergosphere, you couldn't stand still, no matter how hard you tried. Space itself is moving, and you're carried with it. This is called frame dragging, and it's a prediction of general relativity. Every rotating object drags space-time around it, but the effect is tiny unless the object is incredibly massive and spinning incredibly fast. For Earth, the frame dragging is measured in milliarcseconds per year. For a rotating black hole, it's extreme. Roger Penrose realized you could extract energy from the ergosphere. Send a particle into the ergosphere, split it into two parts, throw one part into the black hole, and the other part escapes with more energy than the original particle had. You've extracted energy from the black hole's rotation. This is called the Penrose process, and it's real. In principle, you could power a civilization by dropping matter into a rotating black hole and harvesting the energy. But there's a limit. As you extract energy, the black hole spins down. Eventually, it stops rotating, and the ergosphere disappears. A black hole can lose up to 29% of its mass through the Penrose process before it stops spinning. That's an enormous amount of energy, equivalent to converting mass to energy with 29% efficiency. Far better than nuclear fusion. Some think this might explain quasars, the brightest objects in the universe. Quasars are supermassive black holes at the centers of galaxies, accreting matter at prodigious rates. They shine so brightly that they outshine their entire host galaxies. Maybe the energy comes not just from accretion, but from extracting the black hole's rotational energy. But there's a problem. The Penrose process requires very specific conditions, and it's not clear if nature can achieve them. Most models of quasar energy generation rely on accretion alone, with magnetic fields channeling the energy into jets. The Penrose process might be a sideshow, or it might not happen at all. Still, the idea is tantalizing. Black holes aren't just destructive. They're potentially useful. If you could control a black hole, you could power an interstellar civilization for billions of years. You could even use it as a gravitational slingshot, accelerating spacecraft to relativistic speeds without expending fuel. Black holes could be the power plants and highways of the far future. Of course, there's the small problem of not falling in. Here's another cosmic mystery: the Sunyaev-Zeldovich effect. When photons from the cosmic microwave background pass through galaxy clusters, they interact with hot electrons in the intracluster gas. The electrons give energy to the photons, shifting them to higher frequencies. This creates a distinctive signature, a distortion in the cosmic microwave background. We use this to detect galaxy clusters, even ones too distant to see directly. The Sunyaev-Zeldovich effect gives us a way to map the distribution of matter in the universe, independent of distance. But there's a puzzle. The effect is stronger than expected. The gas is hotter, denser, than our models predict. Why? Maybe galaxy clusters are more turbulent than we thought. Maybe there's energy input from supermassive black holes, from supernovae, stirring the gas and heating it. Maybe our models of cluster formation are incomplete. Or maybe it's telling us something about dark matter, about how it interacts with ordinary matter. This isn't a crisis, but it's a tension. The universe is slightly different from what we predicted, and understanding why matters. Every discrepancy is a clue, and if we follow enough clues, we might uncover something fundamental. Let's discuss antimatter. For every particle, there's an antiparticle. Anti-electrons, antiprotons, antineutrinos. When matter and antimatter meet, they annihilate, converting mass into pure energy. This is the most efficient energy source possible, with 100% conversion of mass to energy. The Standard Model predicts that the Big Bang should have created equal amounts of matter and antimatter. But if that's true, they should have annihilated each other, leaving only photons. The universe should be empty, yet here we are. There's matter, lots of it, and very little antimatter. This is called the baryon asymmetry problem, and it's one of the deepest mysteries in cosmology. Something violated the symmetry between matter and antimatter. Somewhere in the first microseconds after the Big Bang, processes occurred that favored matter over antimatter, creating a tiny excess, one extra matter particle for every billion matter-antimatter pairs. That tiny excess is everything. It's us. It's the stars, the planets, the galaxies. The rest annihilated, and the leftover matter became the universe we see. But what caused the asymmetry? We know of processes that violate charge parity symmetry, creating a preference for matter. Quarks decay slightly differently from antiquarks. Neutrinos oscillate differently from antineutrinos. But the amount of CP violation we've observed isn't enough to explain the baryon asymmetry. Not even close. There must be other sources, other processes, operating at higher energies than we've probed. Maybe grand unified theories, which merge the electromagnetic, weak, and strong forces at extremely high energies. Maybe leptogenesis, where heavy neutrinos decay asymmetrically, creating an excess of leptons that later converts to baryons. Maybe something involving the Higgs field or inflation or physics beyond the Standard Model. We don't know, and it's frustrating because the answer is baked into the universe. It happened. We're the proof. We just don't know how. Some have proposed that there are antimatter galaxies, regions of the universe made entirely of antimatter, separated from matter regions by vast voids. If matter and antimatter never meet, there's no annihilation, no problem. But we don't see evidence for this. Annihilation at the boundaries between matter and antimatter regions would produce a characteristic gamma-ray signature, and we don't see it. The universe seems to be made almost entirely of matter. Almost. We do find antimatter created in high-energy processes, cosmic rays, supernovae, particle collisions in accelerators. But it's always produced alongside matter, and it doesn't last long. It annihilates with the surrounding matter in microseconds. Antimatter is ephemeral, a ghost of symmetry past. Unless we make it ourselves, we can produce antiprotons, positrons, even antihydrogen atoms in particle accelerators. We've trapped antimatter, studied its properties, confirmed that it behaves exactly like matter except for its charge. Antimatter falls down in gravity, not up. It has the same mass, the same quantum numbers. It's not exotic. It's normal, just rare. But storing antimatter is hard. It annihilates on contact with matter, so you have to levitate it with magnetic or electric fields. You have to keep it in a perfect vacuum, isolated from walls, air, dust. The longest we've kept antimatter trapped is about a year, and that was a handful of antiprotons. Making enough antimatter to power a spacecraft, as in science fiction, would require energy inputs far beyond anything we can imagine. It's theoretically possible, but practically absurd. Still, antimatter exists, and it's a window into the early universe. If we could understand why matter won, we'd understand a crucial chapter in cosmic history. We'd know why we exist. Here's a thought experiment that's become a real experiment: the quantum delayed choice entanglement swap. It takes the weirdness of quantum mechanics and amplifies it. You entangle two pairs of particles, A and B, C and D. Then you perform a measurement on B and C, entangling them. This retroactively creates entanglement between A and D, even though they never interacted. Now delay the measurement on B and C until after measurements on A and D have been made. The results for A and D show correlations that shouldn't exist because they weren't entangled when measured. But they become retroactively entangled after the fact. This has been done in labs. It works, and it's profoundly strange. It means that quantum correlations can be created after the fact, that the order of events doesn't matter in the way we classically think it does. Causality is negotiable in quantum mechanics. What does this mean for the nature of time? For the nature of reality? If the past can be changed by future measurements, then the past isn't fixed. It's contingent, probabilistic, waiting to be determined by what we do later. Reality is a tapestry woven from both ends, past and future braided together, and the present is just where they meet. This isn't metaphysics. This is physics, and it suggests that our intuitions about time, causality, reality are wrong. We live in a universe far stranger than common sense allows. Let me tell you about cosmic inflation in more detail. In the first fraction of a second after the Big Bang, the universe underwent exponential expansion. Space doubled in size, then doubled again and again and again 60 times in 10 to 32 seconds. A region smaller than an atom expanded to the size of a grapefruit, then to the size of a galaxy, then to something incomprehensibly large. Inflation explains why the universe is so flat, so uniform, why the cosmic microwave background has the same temperature in all directions. It explains the large-scale structure, the distribution of galaxies. Tiny quantum fluctuations, stretched to cosmic scales by inflation, became the seeds of structure, the slight overdensities that gravity amplified into galaxies and clusters. But inflation creates problems. What drove it? A field called the inflaton, but what is that field? Where did it come from? Why did it start inflating? Why did it stop? We have models, dozens of them, but no definitive answer. And inflation might be eternal. Once it starts, quantum fluctuations ensure it never fully stops. Inflation continues in some regions, while in others it stops and normal expansion takes over, creating pocket universes. Our observable universe is one such pocket, but there are infinitely many others, each with its own properties, its own laws. This is the multiverse again. And if inflation is eternal, the multiverse is not just large, it's infinite. Anything that can happen does happen somewhere. Every possible universe exists. You exist in infinitely many versions with infinitely many variations. There are universes where you made different choices, where history unfolded differently, where the constants of nature are different. Some find this idea liberating. Others find it horrifying. If everything happens, then nothing is special. Your choices don't matter because all choices are made in some universe. Morality becomes arbitrary. Meaning dissolves. But maybe that's wrong. Maybe meaning is local. It matters here, in this universe, even if it doesn't matter cosmically. Your choices affect this world, this timeline, this branch of reality. That's enough. Or maybe the multiverse doesn't exist. Maybe inflation isn't eternal. Maybe there's only one universe, ours, and the appearance of fine-tuning is a cosmic coincidence, or the result of a deeper theory that picks out this universe uniquely. We don't know. What we do know is that inflation explains the data better than any alternative. It predicts the pattern of fluctuations in the cosmic microwave background with stunning accuracy. It's the best theory we have, but it's incomplete and it raises as many questions as it answers. Let's talk about magnetic fields. They're everywhere. Earth has one, the sun has one, galaxies have them, galaxy clusters have them. Even the intergalactic medium has weak magnetic fields. But where do they come from? For Earth, it's the dynamo effect. Convection in the liquid iron core generates electric currents, which create magnetic fields, which twist and amplify through feedback. It's a self-sustaining process, powered by heat from radioactive decay and leftover heat from Earth's formation. But for galaxies, it's more complicated. Galaxies have coherent magnetic fields, aligned along spiral arms, with strengths around a few microgauss. That doesn't sound like much, but spread over tens of thousands of light years, it's a huge amount of magnetic flux. How did it get there? The leading theory is the galactic dynamo. Stars, supernovae, and turbulent gas motions twist and amplify weak seed fields. Over billions of years, this builds up to the observed field strengths. But it requires seed fields to start with, and we don't know where those come from. Maybe they were created in the early universe shortly after the Big Bang. Maybe they're relics of phase transitions or cosmic inflation. Maybe they were generated by the first stars, by battery processes where charged particles separate in ionized plasma. All of these mechanisms could contribute, but none fully explains the observations. And then there are magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's. These fields are so intense that they warp the vacuum, affecting the orbits of electrons, distorting atoms. If you were within 1,000 kilometers of a magnetar, its magnetic field would kill you by disrupting the molecular bonds in your body. How do magnetars get such strong fields? Maybe they're born that way, forming when a massive star with a strong field collapses. The field lines are compressed, amplifying the field. Or maybe dynamo processes in the newborn neutron star, powered by rapid rotation, amplify the field. We've observed magnetars spinning down, releasing energy through magnetic braking. Some produce giant flares, eruptions that briefly outshine entire galaxies in gamma rays. One such flare, from SGR 1806 to 20 in 2004, was the brightest event ever observed from outside the solar system. In a tenth of a second, it released more energy than the sun emits in 150,000 years. If it had been within 10 light years of Earth, it would have caused a mass extinction. Magnetars are extreme, violent, and beautiful. They're laboratories for physics we can't replicate anywhere else. And they're reminders that the universe is capable of things we can barely imagine. Here's something that sounds like fantasy but is mathematical reality. Closed time-like curves in general relativity. These are paths through space-time that loop back on themselves, allowing travel to the past. Einstein's equations permit them under certain conditions. Rotating black holes, traversable wormholes, infinitely long rotating cylinders, cosmic strings under tension. None of these configurations exist naturally as far as we know. And even if they did, actually using them for time travel requires exotic matter, matter with negative energy density, which violates all known energy conditions. So time travel to the past is probably impossible, but probably isn't definitely. And the fact that general relativity allows it, even in principle, is disturbing. It means our best theory of space-time doesn't prohibit time travel. It suggests that causality is a feature of specific space-time configurations, not a fundamental law. Stephen Hawking proposed a chronology protection conjecture. The laws of physics conspire to prevent time travel, even when general relativity seems to allow it. Quantum effects, vacuum fluctuations, should blow up to infinite density whenever a closed time-like curve tries to form, preventing the formation of time machines. But this is speculative. We don't have a full theory of quantum gravity to test it. Maybe time travel is possible. Maybe the universe is filled with closed time-like curves, and causality is an illusion, a local approximation that breaks down on cosmic scales. Or maybe time has a structure we don't understand, something deeper than the timeline of relativity or the parameter of quantum mechanics. Maybe time is emergent from something more fundamental, and the possibility of time travel is an artifact of treating time as fundamental when it's not. We don't know, and every time we think we've understood time, it slips away, revealing deeper layers of mystery. Let's discuss the cosmic neutrino background. We've detected the cosmic microwave background, photons from 380,000 years after the Big Bang. But there should also be a cosmic neutrino background, neutrinos from 1 second after the Big Bang, when the universe was a hot, dense plasma. These neutrinos have been traveling through space for nearly 14 billion years. They've cooled to a fraction of a degree above absolute zero. They're everywhere, about 300 per cubic centimeter, passing through you, through the Earth, through everything. But we've never detected them. Why? Because they're too low energy. The cosmic neutrino background neutrinos have energies around 10 to 4 electron volts, far below the threshold of any detector we've built. Detecting them would require a detector the size of a planet or a revolutionary new technology. But they're out there, and they carry information about the first second of the universe, a time when the cosmos was too hot and dense for photons to travel freely. The cosmic neutrino background is a snapshot of the universe at 1 second old, a window into an era we can't observe any other way. If we could detect it, we'd learn about the number of neutrino species, the total neutrino mass, the conditions in the early universe. We might even see imprints of physics beyond the standard model, new particles or interactions that existed in the first moments. It's one of the great challenges of experimental physics. How do you detect something that barely interacts at energies too low to measure? The answer might involve quantum sensors, superconducting detectors cooled to microkelvin temperatures, or techniques we haven't invented yet. But someone will figure it out. Eventually, we'll detect the cosmic neutrino background. And when we do, it'll be another triumph, another window opened, another piece of the cosmic puzzle. Let me tell you about quasars. They're the brightest, most distant objects we can see, powered by supermassive black holes at the centers of galaxies. Some quasars are so luminous that they outshine a trillion suns. They're visible across billions of light years. But here's the puzzle. Quasars existed when the universe was young, less than 1 billion years old. Supermassive black holes with millions or billions of solar masses were already in place. How? Black holes form from collapsing stars, which have masses of tens of suns. Even if a black hole ate constantly, it would take billions of years to reach supermassive sizes. But the universe wasn't billions of years old yet. Did black holes form differently in the early universe? Maybe there were direct collapse black holes, regions of gas that collapse straight to black holes without forming stars first. Maybe primordial black holes, formed in the first moments after the Big Bang, acted as seeds. Maybe black holes merged rapidly, building up mass faster than we thought possible. We don't know. Every model has problems. Direct collapse requires very specific conditions. Primordial black holes are hypothetical. Mergers are too slow to explain the largest early quasars. And quasars are diverse. Some are radioloud, blasting jets of particles at near light speed. Others are radio quiet. Some are obscured by dust. Others are naked, visible in optical and UV. Some vary on timescales of days, implying that the emission region is light days across. Others are steady. We've learned a lot about quasars, but they still surprise us. We're finding quasars at higher and higher redshifts from earlier and earlier epochs. Each one raises the question, how did you get so massive so fast? And quasars had a profound effect on cosmic history. Their radiation ionized gas in the early universe, clearing out neutral hydrogen, creating bubbles of ionized plasma that eventually merged. This is called reionization, and it transformed the universe from opaque to transparent. Quasars were beacons, lighthouses illuminating the cosmic dark ages. But reionization itself is a mystery. When did it happen? How long did it take? Was it driven by quasars? Or by stars? Or by both? Observations suggest it was patchy, inhomogeneous, with some regions ionized earlier than others. The cosmic microwave background shows the imprint of reionization, but the details are unclear. We're building new telescopes like the James Webb Space Telescope to study the epoch of reionization in detail. We want to see the first galaxies, the first quasars, the first stars. We want to watch the universe wake up, transitioning from darkness to light. And we're close. The data is coming in. The picture is getting clearer. But as always, every answer raises new questions. Here's one that bothers me, the Hubble tension. The Hubble constant describes how fast the universe is expanding. We can measure it in two ways. Locally, using distances to nearby galaxies and their recession speeds, and cosmologically, using the cosmic microwave background and our model of the universe's history. These two methods give different answers. The local measurement says the universe is expanding at about 73 kilometers per second per megaparsec. The cosmological measurement says 67. That's a 9% difference, and it's statistically significant. It's not going away. Is it a problem with one of the measurements? Are there systematic errors we haven't accounted for? Or is it telling us something fundamental, that our model of the universe is wrong? Maybe dark energy is more complicated than we thought, evolving over time instead of being constant. Maybe there's new physics in the early universe, altering the expansion history. Maybe gravity behaves differently on cosmological scales. Or maybe it's something simpler, an error in how we measure distances. The Hubble tension is unresolved. and it's causing sleepless nights for cosmologists. Because if it's real, if our model is wrong, then we don't understand the universe as well as we thought. And that's exciting because it means there's room for discovery. But it's also frustrating because we've spent decades building a standard model that works beautifully, explaining everything from the Big Bang to the formation of galaxies. And now there's a crack, and we don't know if it's a fatal flaw or a minor issue. Time will tell. More data, better measurements will either resolve the tension or confirm it. And if it's confirmed, cosmology will enter a new era where we have to rethink our assumptions, explore new models, push beyond the standard paradigm. That's how science works. Anomalies drive progress. Contradictions point the way forward. And the Hubble tension might be the most important contradiction in cosmology today. Let me tell you about gravitational waves in more detail. When massive objects accelerate, they create ripples in space-time, waves that propagate at the speed of light. Einstein predicted them in 1916, but we didn't detect them until 2015, when LIGO observed two black holes colliding. That detection was a triumph, a confirmation of general relativity in a regime we'd never tested before. It opened a new window on the universe. We're now detecting gravitational waves regularly. Black hole mergers, neutron-star collisions, maybe even exotic events we haven't identified. But gravitational waves are weak. The LIGO detectors are sensitive enough to measure distortions in spacetime smaller than 1,000th the width of a proton. It's an engineering marvel, using lasers, mirrors, and kilometers-long vacuum tubes to detect ripples from collisions billions of light-years away. And what we're finding is surprising. Black holes are more common than we thought, and they merge more often. The masses are strange, some much heavier than expected, others in ranges that shouldn't exist according to stellar evolution models. We're seeing systems that challenge our understanding of how stars die, how black holes form, how they pair up and merge. Neutron-star collisions are even more interesting. When two neutron stars merge, they produce gravitational waves, gamma-ray bursts, and optical transients called kilonovae. We've observed this once in 2017, and it was spectacular. We detected the gravitational waves first, then the gamma rays seconds later, then optical and infrared emission from the expanding debris. The kilonova was bright, visible for weeks, and spectroscopy revealed signatures of heavy elements. Gold, platinum, uranium. These elements are forged in neutron-star mergers, in the intense conditions when matter is compressed to nuclear density and then explodes outward. Every gold atom in your jewelry was created in a neutron-star collision, somewhere, sometime in the history of the universe. That's profound. You're wearing stardust not just from ordinary stars, but from the most violent collisions in the cosmos. The universe had to destroy stars to create the elements that make up your world. Gravitational waves also travel unimpeded through the universe. Unlike light, they're not absorbed, scattered, or blocked. They carry information from regions we can't see electromagnetically. We can use them to probe the interiors of neutron stars, to test general relativity in extreme conditions, to search for exotic objects like cosmic strings or primordial black holes. And we're just getting started. Future detectors, space-based ones like LISA, will be sensitive to lower-frequency gravitational waves from supermassive black hole mergers, from the early universe, maybe even from cosmic inflation itself. We might detect a stochastic background of gravitational waves, a hum from countless unresolved sources, revealing the gravitational history of the cosmos. Gravitational wave astronomy is in its infancy. A century from now, it'll be routine, and who knows what we'll discover. Here's a paradox that doesn't get enough attention: the black hole entropy problem. Entropy is a measure of disorder, of how many ways you can arrange a system's components. For ordinary matter, entropy scales with volume. A bigger box of gas has more entropy. But for black holes, entropy scales with area, specifically the area of the event horizon. This is the Bekenstein-Hawking entropy formula, and it's weird. Why should entropy depend on surface area instead of volume? The answer might lie in the holographic principle. If information is encoded on the horizon, then the entropy naturally scales with area. The black hole's interior doesn't add to the entropy because the information is all on the surface. But this raises questions. What about the interior? If information is on the horizon, what's inside? Some argue the interior doesn't exist, that it's an illusion, a trick of perspective. What we think is the inside of a black hole is actually encoded on the outside. This sounds absurd, but string theory supports it. In ADS/CFT, a black hole in a higher dimensional space is equivalent to a quantum state on the boundary of that space. The interior emerges from correlations in the boundary theory. Space itself is holographic. If this is true universally, then our three-dimensional space might be a hologram. Everything we see, every depth, every dimension, is encoded on a two-dimensional surface at the edge of the universe. We're shadows cast by information living in fewer dimensions. This is the holographic principle, and it's one of the strangest ideas in modern physics. It suggests that dimensionality is negotiable, that space is emergent, that reality has layers we haven't begun to understand. And it connects to entropy in deep ways. The maximum entropy of any region of space is proportional to its surface area, not its volume. This is the Bekenstein bound, and it constrains how much information can be packed into a region. If you exceed the bound, the region collapses into a black hole. This has implications for computation, for information theory, for the ultimate limits of knowledge. You can't know everything about a region of space because there's a maximum amount of information that can exist there. The universe has built-in limits, boundaries beyond which knowledge becomes impossible. And that's humbling. We're exploring a universe that might be fundamentally incompressible, irreducible, where some questions can never be answered not because we're not smart enough, but because the answers don't exist. Let me end this with a thought about our place in all of this. We're insignificant, cosmically speaking, tiny specks on a tiny world, orbiting an average star, in a galaxy that's one of hundreds of billions. The universe doesn't need us. It got along fine for 13.8 billion years before we appeared, and it'll continue just fine after we're gone. But we're also remarkable. We're the universe's way of knowing itself. Atoms forged in stars, arranged into patterns complex enough to contemplate their own existence. We've figured out where we came from, how old the universe is, what it's made of. We've seen the echoes of the Big Bang. We've detected gravitational waves from colliding black holes. We've walked on the moon. We've done all this in the cosmic equivalent of an eye blink. Civilization is 10,000 years old. Science is 400. And in that time, we've gone from thinking the Earth was flat to mapping the entire observable universe. Imagine what we might accomplish in the next 400 years. The next 4,000. If we survive, if we keep asking questions, keep exploring, keep pushing the boundaries, what might we discover? Maybe we'll solve the paradoxes. Maybe we'll find the theory of everything, uniting quantum mechanics and general relativity. Maybe we'll understand consciousness, time, existence itself. Or maybe we'll find that the universe is deeper than we ever imagined, that every answer reveals infinite questions, that the mystery never ends. Either way, the journey is worth it. Because in asking these questions, in confronting these paradoxes, we're doing something extraordinary. We're participating in the universe's self-discovery. We're part of the cosmic story. And that's enough. That's everything. The paradoxes will keep us awake at night. The mysteries will haunt us. The universe will remain strange, beautiful, terrifying, incomprehensible. But we'll keep looking up. We'll keep asking why. And maybe, just maybe, we'll find answers that transform everything we thought we knew. The cosmos is vast. The questions are endless. And we're here, wondering, exploring, reaching for truths that shimmer just beyond our grasp. That's what it means to be human. That's what it means to be alive in this particular corner of space-time, in this brief moment between the Big Bang and heat death, when stars still shine and minds can still wonder. So embrace the paradoxes. Let them drive you forward, because every paradox is an invitation, and the universe is waiting to show you something you've never seen before. Now let me take you deeper into quantum mechanics, to a place where reality itself becomes negotiable. The double-slit experiment. You've probably heard of it, but let me tell you why it should shake you to your core. Send a single electron toward a screen with two slits. Common sense says it goes through one slit or the other, but it doesn't. It goes through both, interfering with itself, creating a pattern on the detector that only makes sense if the electron was in two places at once. Watch which slit it goes through and the pattern changes. The interference disappears. The electron behaves like a particle, not a wave. The act of observation changes what happens. Not because you disturbed it mechanically, but because measurement itself is a physical process that collapses possibilities into actualities. This isn't a metaphor. This is what actually happens. And we've done it with molecules, with large organic compounds containing hundreds of atoms. We've done it with light, with neutrons, with entire systems. The quantum world doesn't care about your intuitions. It follows rules that seem designed to make philosophers weep. But here's what really keeps me up: the implications for reality. Before measurement, the electron isn't secretly in one place that we just don't know about. It's genuinely in a superposition, existing in multiple states simultaneously. The wave function is real, not just a mathematical convenience. And when you measure, something happens. The superposition collapses. But what causes the collapse? What singles out one outcome from many? Nobody knows. And that's after a century of quantum mechanics. We can calculate probabilities with extraordinary precision. We can build technologies that exploit quantum effects. But we can't explain what happens during measurement. It's called the measurement problem, and it's the dirty secret at the heart of physics. Some say there's no collapse. The universe branches and all outcomes occur in parallel universes. Some say consciousness causes collapse. Some say decoherence explains it, that interaction with the environment naturally destroys superpositions. But none of these explanations is fully satisfying. They all have problems, conceptual or mathematical. And this matters because if we don't understand measurement, we don't understand observation. And if we don't understand observation, we don't understand the relationship between reality and knowledge. We don't understand what it means to know something about the world. Let's talk about dark matter candidates more specifically. We know dark matter exists. We see its gravitational effects. But what is it? The leading candidate is WIMPs, weakly interacting massive particles. They'd be heavy, around 10 to 1,000 times the mass of a proton, and they'd interact only through gravity and the weak nuclear force. Dozens of experiments have searched for WIMPs. They use detectors buried deep underground, shielded from cosmic rays, cooled to near absolute zero, waiting for a WIMP to collide with a nucleus. It would happen maybe once a year in a ton of material. And so far, after decades of searching, we've found nothing. Not a single confirmed detection. Maybe WIMPs are lighter than we thought, or heavier, or interact even more weakly. Maybe they're not WIMPs at all. Maybe they're axions, hypothetical particles predicted by solutions to the strong CP problem. Axions would be incredibly light, billions of times lighter than electrons, and they'd interact primarily with photons in strong magnetic fields. We're looking for axions too, using resonant cavities in magnetic fields, searching for the faint photons that would be produced if axions convert to photons. Again, nothing confirmed. The parameter space is vast, and we're searching methodically, but it's like looking for a specific grain of sand on all the beaches of Earth. Or maybe dark matter is primordial black holes, formed in the first moments after the Big Bang. Not from collapsing stars, but from density fluctuations in the early universe. These could have any mass, from microscopic to thousands of solar masses. They'd be invisible, interacting only through gravity, which is exactly what dark matter does. But there are constraints. If dark matter were primordial black holes of certain masses, we'd see effects we don't see. Gravitational lensing of distant stars, disruption of wide binary star systems, effects on the cosmic microwave background. Most mass ranges are ruled out. Only a few windows remain open, and even those are controversial. Maybe dark matter isn't particles at all. Maybe it's a modification of gravity. Mond, modified Newtonian dynamics, proposes that gravity behaves differently at very low accelerations, producing effects that mimic dark matter. It works surprisingly well for galaxy rotation curves, but it fails for galaxy clusters, for the cosmic microwave background, for the large-scale structure of the universe. It's not a complete theory. Or maybe dark matter is something exotic. Mirror matter, hidden sectors, dark photons, sterile neutrinos. The possibilities are endless, constrained only by observations and theoretical consistency. We're feeling around in the dark, literally trying to identify something we can't see by its absence, by the holes it leaves in our understanding. It's frustrating, it's exhilarating, and it's the frontier of particle physics. Somewhere in the data, in the null results and the anomalies, is a clue. We just have to recognize it. Here's a cosmic mystery that touches on the nature of causality. Retrocausality. It's the idea that effects can precede causes, that the future can influence the past. This sounds like science fiction, but certain interpretations of quantum mechanics allow for it. In the transactional interpretation, particles exchange advanced and retarded waves, solutions to the wave equation that propagate forward and backward in time. The transaction, the physical event, is the handshake between these waves. Cause and effect become symmetric, neither fully preceding the other. In the two-state vector formalism, quantum states are described by both a forward-evolving state from the past and a backward-evolving state from the future. The present is determined by both. Your future affects your past, and your past affects your future in a time-symmetric dance. These aren't mainstream views, but they're taken seriously by some physicists because they solve certain problems in quantum mechanics. They eliminate the need for wave function collapse. They explain the EPR paradox naturally. They make sense of the delayed choice experiments. But they require accepting that time doesn't flow the way we think it does, that cause and effect are more flexible than classical intuition allows. And that's a hard pill to swallow, even for physicists who deal with quantum weirdness daily. If retrocausality is real, what does it mean for free will? If your future choices affect your past, are you free? Or are you trapped in a self-consistent loop, where the future determines the past, which determines the future. Is time a circle or a line or something else entirely? We don't know. And maybe we can't know because our brains evolved to navigate a world where causes precede effects, where time flows forward, where the past is fixed and the future is open. We're trying to understand physics that violates these assumptions, using minds shaped by those assumptions. We might be fundamentally limited, or maybe we'll adapt. Maybe future humans, augmented by technology or evolution, will think naturally in terms of retrocausality of time-symmetric physics. Maybe they'll look back at us and wonder how we ever managed with such a primitive understanding of time. Let's discuss cosmic voids in more detail. The universe isn't uniform. Galaxies cluster into groups, clusters, superclusters, arranged in filaments and sheets. And between these structures are voids, vast regions containing very few galaxies. The largest known void is the Boötes void, discovered in 1981, about 330 million light-years in diameter. It contains only about 60 galaxies, compared to the 2,000 you'd expect in such a volume. It's not completely empty, but it's remarkably underdense. What created the voids? Gravity. In the early universe, matter was almost uniformly distributed with tiny fluctuations. Gravity amplified these fluctuations. Overdense regions attracted more matter, becoming denser. Underdense regions lost matter, becoming emptier. Over billions of years, this process created the cosmic web, dense filaments surrounding voids. But voids aren't static. They're expanding faster than the average expansion of the universe. Galaxies are streaming away from void centers, piling up on void edges. This creates a peculiar velocity field, a pattern of motion superimposed on the Hubble flow. And voids might tell us about dark energy. The expansion of voids is sensitive to the nature of dark energy, to whether it's constant or evolving. By mapping voids, measuring their sizes and expansion rates, we can constrain models of dark energy. Some have proposed using voids as cosmological laboratories. They're pristine environments, relatively unaffected by the complex astrophysics of galaxies and clusters. Studying voids might reveal subtle effects that are washed out in denser regions. There's even speculation about void-dwelling civilizations. If you wanted to avoid cosmic hazards, supernovae, gamma-ray bursts, radiation from quasars, you'd build your civilization in a void. You'd have clear skies, low backgrounds, perfect isolation. Of course, you'd also have fewer resources, fewer nearby stars to colonize. But maybe that's a worthwhile trade-off. We haven't found any evidence of civilizations in voids, but we haven't looked hard. And if they're there, staying quiet, we might never know. Now let me tell you about the Unruh effect. If you accelerate through empty space, you'll detect thermal radiation, a bath of particles that isn't there for stationary observers. The harder you accelerate, the hotter the radiation. It's called the Unruh effect, and it's a direct consequence of quantum field theory in curved spacetime. For an observer accelerating at the acceleration of Earth's gravity, the Unruh temperature is about 4x 10 to minus 20 Kelvin. That's immeasurably small. But for an observer accelerating at 10 to 20 m/s2, about what you'd experience near the event horizon of a stellar mass black hole, the temperature is about 1 Kelvin. That's measurable, at least in principle. The Unruh effect is deeply connected to Hawking radiation. From the perspective of an accelerating observer, the vacuum is full of particles. From the perspective of a stationary observer, those particles don't exist. Reality depends on your acceleration, on your reference frame. This has profound implications. It means that particles, the basic constituents of matter, are observer-dependent. What's empty space for one observer is a thermal bath for another. The vacuum isn't a fixed thing. It's relative, contingent, dependent on motion. And if particles are observer-dependent, what does that say about reality? Is there an objective universe? Or is everything perspectival, dependent on who's looking and how they're moving? Some physicists argue that this shows particles aren't fundamental. Fields are fundamental. Particles are excitations of fields, and which excitations exist depends on how you slice up the field, which depends on your reference frame. Particles are convenient fictions, patterns we impose on a more fundamental reality. But this is unsettling. We think of particles as real, as things that exist independently of observation. The Unruh effect says that's wrong. Existence itself is frame-dependent, and we've never directly detected the Unruh effect. It's too small for any acceleration we can produce in a lab. But we've detected Hawking radiation's analog in acoustic systems, in fluids, in condensed matter systems. These analog gravity experiments suggest the Unruh effect is real, that the mathematics works. But we'd like to see it directly in actual particles, in actual vacuum. Maybe someday. Technology advances, experiments get more precise. Or maybe we'll never see it, and it'll remain a theoretical curiosity, a consequence of quantum field theory that we trust but can't directly confirm. Let's talk about planet formation. We have a decent understanding of how planets form. Gas and dust in a protoplanetary disk collide, stick together, grow. Small grains become pebbles. Pebbles become boulders. Boulders become planetesimals. Planetesimals become planets. Gravity takes over when objects get large enough, accelerating the process. But there are problems. The meter-size barrier. For one, meter-sized objects in a disk experience strong drag from gas. They should spiral into the star in a few hundred years, never growing large enough to become planets. Yet planets exist. We're standing on one. The solution might be streaming instabilities, where pebbles concentrate locally, forming clumps that collapse directly into planetesimals. Or maybe pebble accretion, where planetesimals grow by accreting small pebbles that are coupled to the gas. These mechanisms can bypass the meter-size barrier, allowing rapid growth. But the details are murky. Simulations struggle to reproduce observed planet systems. We find hot Jupiters, massive planets orbiting close to their stars, where they shouldn't be. We find super-Earths, planets larger than Earth but smaller than Neptune, which don't exist in our solar system. We find systems with planets in orbital resonances, synchronized like clockwork, and systems with chaotic orbits, planets on the brink of ejection. The diversity of exoplanet systems is staggering. Every one is different. Some have multiple planets. Some have one. Some have debris disks. Some are bare. The more we discover, the more we realize our solar system isn't typical. It's one outcome among many, maybe even unusual. And there are mysteries within our own solar system. Why is Mars so small? It's in the right location to be a large planet between Earth and Jupiter. But it's tiny, barely a tenth of Earth's mass. Something stunted its growth. Maybe Jupiter's gravity stirred the asteroid belt, preventing planetesimals from accreting into Mars. Maybe Mars lost mass through collisions. We're not sure. Why doesn't Venus have a moon? Earth has one formed from a giant impact. If Venus experienced a similar impact, where's its moon? Maybe it did have a moon and it spiraled in, crashing into Venus. Maybe the impact that formed Venus's moon was different, producing a satellite that didn't survive. Why is Earth's water so abundant? Water is volatile, easily evaporated in the hot inner solar system. Earth should be dry, but it's not. Maybe asteroids brought water. Maybe comets. Maybe water was trapped in minerals, released later by volcanism. Or maybe Earth formed far from the sun and migrated inward, preserving its water. These are questions about our own cosmic backyard, and we're still figuring them out. Here's something strange about pulsars. They're rotating neutron stars, beaming radiation from their magnetic poles. As they spin, the beams sweep across space like lighthouses. If Earth is in the beam's path, we see pulses, regular as clockwork. Some pulsars pulse thousands of times per second, but pulsars slow down. They lose rotational energy, emitted as electromagnetic radiation and particle winds. Eventually, they spin too slowly to emit, and they disappear from view. This is called the pulsar graveyard, and it's full of dead neutron stars, invisible, spinning silently through space. Except some pulsars speed up. They glitch, sudden increases in rotation rate. The interior of the neutron star, a superfluid of neutrons, transfers angular momentum to the crust. It's like a cosmic ice skater pulling in their arms, spinning faster. But how does this happen? The interior and crust are coupled, but not perfectly. The superfluid can rotate faster than the crust, storing angular momentum. When the two phases reconnect, angular momentum transfers suddenly, causing a glitch. We've observed thousands of glitches, but we don't fully understand the mechanics. The interior of a neutron star is extreme, with densities higher than atomic nuclei, pressures beyond anything in terrestrial labs. Matter behaves in ways we can't replicate, governed by physics we can't fully compute. Neutron stars might have quark cores, regions where neutrons dissolve into their constituent quarks. They might have pion condensates, strange phases of nuclear matter. They might have crusts made of exotic nuclei, neutron-rich isotopes that don't exist on Earth. Every pulsar is a natural laboratory, testing theories of nuclear physics, of superfluidity, of magnetic fields. And they're giving us data we can't get any other way. There's also the pulsar timing array, a network of pulsars across the sky that we monitor with exquisite precision. Pulsars are such accurate clocks that we can use them to detect gravitational waves. When a gravitational wave passes between Earth and a pulsar, it stretches space, changing the arrival time of pulses. By monitoring many pulsars, we can detect waves that individual detectors can't see. And recently, pulsar timing arrays have found evidence of a gravitational wave background, a stochastic hum from countless sources. Merging supermassive black holes, cosmic strings, maybe the early universe itself. It's a new window, a new way of seeing the cosmos, and we're just beginning to interpret what we're hearing. Let me tell you about rogue planets. Not all planets orbit stars. Some were ejected from their parent systems, flung into interstellar space by gravitational interactions. They wander the galaxy, dark, cold, invisible. We've found a few rogue planets, mostly through microlensing, where a planet passes in front of a background star and briefly magnifies its light. But they're hard to detect. No starlight to reflect, no infrared emission unless they're young and still cooling. They're ghosts. How many rogue planets are there? Estimates vary wildly, from 1 per star to 10 per star. If the upper estimate is right, there are more rogue planets than stars in the galaxy. Hundreds of billions of worlds, drifting alone, never to see a sunrise. Could life exist on rogue planets? Probably not, but maybe. If a planet is massive enough, it could retain heat from its formation, from radioactive decay, from tidal flexing if it has a moon. Subsurface oceans, heated from below, might persist for billions of years. Life, if it arose before ejection, might survive in those oceans, cut off from the cosmos, unaware of stars or galaxies. It's a melancholy thought. Civilizations on rogue planets would have no astronomy, no way to know about the larger universe. They'd think they're alone, adrift in infinite darkness. Would they despair, or would they find meaning in their isolation? We'll probably never know. Rogue planets are too numerous, too distant, too dark to study in detail. They're out there, a hidden population, a reminder that the galaxy is stranger and more diverse than we imagine. Now let's discuss the Planck scale, the smallest meaningful length in physics, about 10 to minus 35 meters. At this scale, quantum fluctuations of spacetime become so intense that the concepts of distance and time break down. Space itself becomes foamy, probabilistic, uncertain. We can't probe the Planck scale directly. It would require energies 10 to 16 times higher than the Large Hadron Collider. We'd need a particle accelerator the size of the galaxy. But we can theorize, and what the theories suggest is radical. At the Planck scale, spacetime might be discrete, quantized, made of tiny loops or strings or networks. Loop quantum gravity proposes that space is woven from quantum loops, interconnected like chainmail. String theory proposes that fundamental particles are vibrating strings, and spacetime emerges from the interactions of these strings. Both approaches suggest that smooth spacetime is an illusion, an approximation that works at large scales but breaks down at small scales. Just as water seems continuous but is made of molecules, spacetime seems smooth but might be made of discrete units. If space is quantized, what does that mean? It means there's a smallest possible distance, a pixel size for reality. It means the universe is fundamentally discrete, like a cosmic computer simulation. It means calculus, which assumes continuity, doesn't apply to the deepest level of nature. But we don't know if space is quantized. We have theories, but no experimental evidence. The Planck scale is so far beyond our reach that we might never test these ideas directly. We're forced to rely on indirect methods. Cosmology, black holes, thought experiments. And there's the problem of quantum gravity. General relativity describes gravity as curved spacetime. Quantum mechanics describes particles and fields, but they're incompatible. General relativity is deterministic, smooth, geometric. Quantum mechanics is probabilistic, discrete, algebraic. Combining them produces infinities, nonsensical results, mathematical breakdowns. String theory and loop quantum gravity are attempts to solve this, but neither is complete. String theory requires extra dimensions, 10 or 11 total, curled up too small to see. It predicts a vast landscape of possible universes, with no clear way to single out ours. Loop quantum gravity avoids extra dimensions but struggles to reproduce general relativity in the appropriate limit. We've been working on quantum gravity for decades, and we're not close to a solution. It might be the hardest problem in physics, requiring insights we haven't had, mathematics we haven't invented, experiments we can't perform. Or maybe the problem is ill-posed. Maybe gravity isn't quantum. Maybe it's classical and quantum mechanics needs to be modified to accommodate it. Maybe there's a third option, something neither quantum nor classical, that we haven't imagined. We don't know, and that uncertainty, that gap in our understanding, is both humiliating and motivating. We've explained so much from quarks to galaxies, but the deepest question, how to unite our two best theories, remains unanswered. Let's talk about the cosmic web in more detail. If you could see the universe on the largest scales, you'd see a web of filaments, sheets, and nodes with voids in between. Galaxies aren't scattered randomly. They're organized, structured, following paths carved by gravity over billions of years. This structure originated from quantum fluctuations in the early universe, inflated to cosmic scales. Overdense regions attracted matter, underdense regions expelled it. Over time, matter flowed into filaments, the paths of least resistance, creating the web. But the cosmic web isn't static. It's evolving. Filaments are thinning as dark energy pulls the universe apart. Voids are growing. Clusters are merging, forming larger structures. Eventually, in the far future, the web will dissolve. Dark energy will have stretched space so much that galaxies lose contact, and the cosmic web becomes a memory, encoded in the motions of isolated galaxies. We can map the cosmic web using galaxy surveys, measuring the positions and distances of millions of galaxies. The patterns we see match predictions from simulations, confirming our understanding of structure formation. But there are anomalies. The cosmic web has structure on scales larger than expected. There are alignments, correlations, that shouldn't exist if the universe is random. Some call this the cosmic axis of evil, though that's an exaggeration. It's more like a hint, a whisper of something we don't understand. Maybe it's a statistical fluke. Maybe it's a sign of new physics, of interactions between our universe and others in a multiverse. Maybe it's telling us about the initial conditions of the Big Bang, about what happened during inflation. We won't know until we have more data. And the cosmic web might contain more than galaxies. There could be gas, ionized plasma, filling the filaments. We've detected some of this gas using quasar absorption lines, seeing shadows where light passes through. But most of it is invisible, too diffuse to detect directly. There might also be dark matter filaments, rivers of dark matter flowing along the web. We can't see dark matter, but we can infer its presence from gravitational lensing, from the bending of light around massive structures. And what we find is that dark matter traces the cosmic web, forming a scaffolding on which galaxies grow. In a sense, we see only the foam on the waves. The real ocean, the dark matter and dark energy, is invisible. We're mapping shadows, inferring a structure we can't directly observe. And yet, we're succeeding. We're piecing together a picture of the universe on the largest scales, and it's beautiful. Here's a mystery closer to home: the dynamo problem. Earth's magnetic field protects us from solar wind, from cosmic rays, from radiation that would strip away our atmosphere and sterilize the surface. Without it, Earth might be like Mars, cold, dry, dead. The field is generated by convection in Earth's outer core, liquid iron flowing, creating electric currents, which generate magnetic fields, which twist and amplify through feedback. It's a dynamo, self-sustaining, powered by heat from the interior. But the details are complicated. The flow in the core is turbulent, three-dimensional, time-varying. It's governed by magnetohydrodynamics, the interaction of fluid flow and magnetic fields, one of the most complex branches of physics. We can't solve the equations exactly. We have to simulate them on supercomputers, and even then, we can only approximate. And Earth's magnetic field does strange things. It flips. Every few 100,000 years, north becomes south, south becomes north. The flips aren't regular. Sometimes they're quick, taking a few thousand years. Sometimes they're slow. Sometimes there are false starts, excursions where the field weakens but doesn't fully flip. The last flip was 780,000 years ago. We're overdue. The field has been weakening for the past 2,000 years, especially over the South Atlantic, where there's an anomaly, a region where the field is unusually weak. Is this the start of a flip? Are we living through the early stages of a magnetic reversal? Probably not. The field fluctuates naturally. The South Atlantic anomaly has existed for centuries, maybe longer. It's not necessarily a precursor to a flip, but it could be. We don't know. If a flip happens, what would we experience? During a flip, the field weakens, perhaps dropping to 1/10 of its current strength. This exposes the surface to more radiation, more cosmic rays. Satellites would be more vulnerable. Power grids might be disrupted by solar storms, but life would survive. The atmosphere provides some protection, and flips have happened hundreds of times in Earth's history without causing mass extinctions. Still, it's unsettling. We depend on the magnetic field, and we don't fully understand it. We can't predict when it'll flip, how fast the flip will occur, or what the consequences will be. We're at the mercy of processes in Earth's core that we can barely observe, let alone control. And other planets have their own magnetic mysteries. Jupiter's field is immensely strong, 20,000 times stronger than Earth's. It's generated by convection in metallic hydrogen, a phase of hydrogen that exists only under extreme pressure, deep in Jupiter's interior. We've never seen metallic hydrogen in a lab. We're not even sure how it behaves, but it's there, generating a field that dominates Jupiter's magnetosphere, stretching millions of kilometers into space. Mercury has a weak field, too weak for its size. Venus has almost no field. Mars had a field but lost it billions of years ago, and its atmosphere was stripped away by solar wind. The Moon once had a field, early in its history, but it's gone now. Why do some planets have fields and others don't? It depends on the interior structure, on whether there's a liquid conducting layer undergoing convection. But the details are murky. We're still figuring out what happens inside planets, what drives their magnetic fields, what determines their fates. Let me tell you about cosmic strings. They're hypothetical defects in space-time, one-dimensional structures formed during phase transitions in the early universe. Think of them as cracks, scars left behind as the universe cooled and symmetries broke. Cosmic strings would be incredibly thin, about the Planck length in diameter, but incredibly massive, with tensions around 10 to 21 kilograms per meter. A piece of cosmic string the length of a proton would weigh as much as Mount Everest. And they'd be long, stretching across the universe, perhaps infinite. If cosmic strings exist, they'd have observable effects. They'd create gravitational lensing, doubling images of distant galaxies. They'd generate gravitational waves, detectable by pulsar timing arrays. They'd seed structure formation, creating filaments of galaxies. They might even create closed time-like curves, allowing time travel. But we haven't found cosmic strings. Searches have turned up nothing. Either they don't exist, or they're rarer than expected, or we're not looking in the right way. Most models of the early universe don't predict cosmic strings, but some do, especially grand unified theories and string theory. If they exist, cosmic strings would be remnants of the universe's infancy, fossils of conditions we can never recreate. They'd tell us about phase transitions, about symmetries, about physics at energies far beyond the reach of accelerators. They'd be treasure troves of information about the first moments after the Big Bang. Or they might not exist at all. The universe might have cooled smoothly without forming topological defects. The early universe might have been simpler than we think, or more complicated in ways that don't involve cosmic strings. Either way, the search continues. Because if cosmic strings are out there, Finding one would be a Nobel Prize-level discovery, a window into physics we can't access any other way. Now let's talk about the horizon problem more deeply. The cosmic microwave background is uniform to within 1 part in 100,000. Every direction looks the same temperature. But according to standard Big Bang cosmology, regions on opposite sides of the sky were never in causal contact. They were too far apart for light to travel between them in the time since the Big Bang. So how did they reach the same temperature? How did they know to be the same? It's like two people on opposite sides of Earth wearing the same outfit without ever communicating. It's too coincidental. Inflation solves this. Before inflation, the universe was tiny, small enough that all regions were in contact. They equilibrated, reaching the same temperature. Then inflation happened, blowing them apart, expanding a tiny patch to become larger than the observable universe. The uniformity we see is a relic of that early contact. But inflation is weird. It requires a field, the inflaton, with very specific properties. And we don't know what the inflaton is. We've looked for it, searched for its particles, its interactions. Nothing. It might be a scalar field like the Higgs. It might be a pseudo-Goldstone boson. It might be something else entirely. And inflation had to start somehow. What triggered it? Quantum fluctuations? A phase transition? Initial conditions? If initial conditions, we've just pushed the problem back. We haven't explained anything. We've replaced why is the universe uniform with why were the initial conditions right for inflation. Some propose eternal inflation, where inflation never fully stops, constantly creating new regions, new universes. But this raises its own problems. Eternal inflation predicts a multiverse, and testing multiverse theories is nearly impossible. We're trapped in one universe. We can't see the others. Alternatives to inflation exist. The ekpyrotic universe, where our Big Bang was a collision between brains in higher dimensional space. Bouncing cosmologies, where the universe contracts, bounces, and expands, cycling eternally. Variable speed of light theories, where light traveled faster in the early universe, allowing distant regions to communicate. None of these alternatives work as well as inflation. They're less predictive, more contrived, harder to test. Inflation is the best theory we have, but it's not perfect. And the horizon problem remains a reminder that the Big Bang isn't the beginning of the story. Something happened before, something that set the stage for everything that followed. Let me close with one final thought. We've covered dozens of paradoxes, dozens of mysteries. The Fermi paradox, the information paradox, the measurement problem, dark matter, dark energy, the arrow of time. Each one is a challenge, a question without a clear answer. But here's what amazes me. We know enough to ask these questions. A century ago, we didn't know about quantum mechanics, about the expanding universe, about black holes. We've learned so much in such a short time. And the paradoxes, the mysteries, they're not signs of failure. They're signs of progress. Every paradox is a gap in our understanding, a place where our theories break down, where reality surprises us. And gaps are opportunities. They're where new ideas emerge, where breakthroughs happen, where paradigms shift. The universe doesn't owe us answers. It doesn't care if we understand it. But it's given us minds capable of asking questions, eyes capable of seeing stars, instruments capable of detecting gravitational waves. It's given us mathematics, logic, curiosity, the ability to wonder. And we're using those gifts. We're exploring, discovering, creating knowledge where none existed before. We're mapping reality one observation at a time, one theory at a time, one breakthrough at a time. The paradoxes will persist. Some might never be solved, but that's okay, because the journey, the process of inquiry, the struggle to understand, that's what makes us human. That's what gives life meaning. We're a species that looks up at the night sky and asks why. And that, more than anything, is what defines us. So keep wondering, keep asking, keep pushing against the boundaries of knowledge. Because out there, in the cosmos, in the quantum foam, in the singularities and horizons and wave functions, are answers we haven't found yet. And maybe, just maybe, you'll be the one to find them. The universe is waiting. The paradoxes are calling. And the greatest discoveries of all time are still ahead of us, waiting for minds brave enough, curious enough, stubborn enough to seek them out. This is COSM Hush, reminding you that reality is stranger than you think. And that's exactly why it's worth exploring.